So good morning, everyone. Welcome to this initiative seminar about cybersecurity. My name is Johansson. I'm the Vice Director of the Chalmers Area of Advance in Information and Communication Technology. We're organizing this seminar. So I just wanted to say a few words about what the Area of Advance is. So it's Chalmers initiatives to promote certain areas of research where we have particularly good research. So we're working cross-departmentally with researchers from computer science, electrical engineering, and physics even. And we're also trying to make connections with industry. And I think there are many representatives from local industry here. You're particularly welcome. So one of the ways we're also working strategically is to focus on particular areas. And with the developments of the world today, the importance of the internet infrastructure, cybersecurity is one such strategic area. And this is why we're organizing this seminar today. So you're very welcome. We have a program of several speakers, both international and local speakers. So I will hand over to my colleague, Andrei Sabelfeld, who will share the first session. Andrei.
Okay, thank you. Thank you, Moa. So, good morning, everybody. My name is Andrei Sabelfeld. I have the pleasure of being the chair of the first session. We are particularly delighted to have excellent speakers today, and it's particularly awesome that Professor David Basin from ETH Zurich will be opening the sessions. So David is really one of the best researchers in the field of cybersecurity, one of the best actors being prominent in academic activities and in industrial connections. And that makes him fit this event extremely well. So he's done a lot of work in cybersecurity, for which he's received a number of awards. So just to mention a couple of them, he's a fellow of ACM. And he received a lot of best paper awards, and he's been serving on top program committees and journal editorial boards. So in Zurich, David is heading Center for Information Security, which kind of connects academia and industry. So hopefully we can learn from some of that experience. And one of the excellent kind of profiles of David is this ability of connecting theory and practice. So building robust solutions that have applications in industrial problems. And hopefully we'll get a flavor of that also in his talk today. So we'll talk about a new internet for real, which will be very exciting to hear about. So please, David.
Thank you very much, Andrei. It's really a pleasure to be here in Göteborg again and to be able to talk at this event, and I hope to meet many of you personally over the next day. So I'll be talking about research at ETH Zurich from myself and a number of groups on building a new internet. I'm going to motivate first why we might want to have a new internet. Then we'll have to understand what some of the root problems of the current internet are. That'll be essential for seeing how we can improve the current situation. And I'll focus on BGP-related vulnerabilities. And finally, the good news is it's not just that the world is a scary place and has problems, but we as researchers can do something about it, and we can do something about it in a way that can help administration and enterprises. Let's begin. So, needless to say, our society today is driven by networked information systems. So whether we're talking about health, communication, energy distribution, defense, transport, even voting and our democratic processes, it all depends on having a functioning, effective, and secure internet. Unfortunately, as the internet has been expanding, as we have increasing number of devices, whether they be desktops or servers in the cloud or IoT devices, as the numbers go up, one invariant is that attacks go up. Here I just have some statistics for DDoS attacks, and the numbers per se aren't really important. You don't have to read the scales. But I want to point out that the numbers are going up, the volume of attacks are going up, no matter how you measure it, and of course the financial losses are going up. Now, we can look at these graphs and say, yes, it looks like a bad thing, but of course, if you're hit by these attacks, it's a very bad thing. I don't have much data on what's happening here in Sweden. I come from Switzerland. I do keep track of what's happening in Switzerland and its neighbors. And without reading all of the different headlines, some in English, some in German, we find that telecommunication companies are being hit by DDoS and other kinds of attacks. So critical services, fire, police, etc., are not working. Financial service institutions, I have some examples of these, are being hit by DDoS attacks. Sometimes they're ransomware based, sometimes they're just designed to take parts of the financial system down. Our cities, our Gemeinde, are being affected, where data is being stolen and websites are being taken offline, especially during critical periods like elections. Even humanitarian organizations like the Red Cross is under attack, and the numbers are increasing. So from a distance, the world may look peaceful. You know, our Zoom sessions typically work, typically email gets across, etc. But if you look closer, you know, if you're on the front lines, you see the situation is a very different thing. The internet is on fire. So that was motivation. Let's now go and look at some of the root causes. And there are actually many different problems in the internet today. For example, clients can be compromised, you can have social engineering attacks, etc. I'm going to focus on one particular class of problems, namely in routing, problems related to the core routing protocol for doing inter-domain routing, and that's BGP. Okay, so we're going to look at that in a little bit of detail, so back to school, but we are at a school. I'd like to explain that to you, and then we'll see what we can do about it. So the underlying protocol for inter-domain routing, how messages get across the internet, is BGP, which is used to configure routers. And if you don't know anything about routing, we can make an analogy with walking through the forest with a compass, where every so often you look at your compass and you see, to get to my destination, I have to turn right. Then later on you see, I have to go left. And this is what BGP does. It's used to configure border routers, hence the border gateway protocol, such that each of them will tell packets how to get a little bit closer to the end destination. So BGP provides no details on the route ahead. It just tells you the next hop, how to configure routers for that. And you have no control and transparency on where your packets go. And this isn't a very good way, for example, to walk through the forest or to send ships through the ocean or to send packets through the internet. Let me look at that in a little bit more detail. So the internet is a network of networks. So these networks that contain, the bigger networks are called autonomous systems. So the nodes in this picture correspond to autonomous systems. And they are organizations that run a set of routers and have the responsibility for administrating them. So this might be a telco or an internet service provider or a company or a university. So my own university, ETH Zurich, is an autonomous system, and it has this particular AS number. A Swiss bank like Credit Suisse might actually be divided into 6 autonomous systems. And so these little circles here represent autonomous systems, and they're scattered throughout the world. And inter-domain routing is about how packets go from one autonomous system to another. Okay, and the packets are sent via routers. And here on one slide is a high-level explanation of what a router does. Abstractly, routers are pretty simple. They have 2 roles in life. It's kind of a boring life being a router. One role is to find paths between autonomous systems. So this is called the control plane, and this is where BGP is important. The other is to forward data along the paths, and this is where their routing tables are used. So here we have a picture where we have 4 autonomous systems. And if you want to route between autonomous system 2 and autonomous system 4, there are multiple paths. The control plane will find, for example, the purple path and the red path, and BGP will be used to select one of these paths for forwarding. So this protocol BGP is used in the background to select paths to configure routers. So what does that look like in a little bit more detail? Here again, the clouds are autonomous systems, and we have a source and a destination. What is happening is that each of these autonomous systems are sending out beacons, and the beacons construct and thereby find paths through the internet. For example, there might be a path going 875.421, And that path might be used to configure all of the different routers so they can know the next hop. And that configuration will be used such that when the source sends information to the destination, the traffic will flow in the opposite direction along these purple links. So BGP finds paths, and the data flows from the source to the destination along those paths. Zooming in a little bit more, but leaving out still the technical details, how does BGP work? So an autonomous system can announce some IP range, some range of internet addresses that it controls. So for example, 8 will initialize a beacon saying, I can reach this IP range, this address range. And that goes to 7, and 7 will send out a beacon, I can reach this IP range, this is sub-range, over AS8, and these beacons are propagated, and that way the various autonomous systems along the way can know how they can end up reaching this IP range, and each of their border routers, the routers for interdomain routing, can be appropriately configured. Now, the policies on which beacons are propagated, which beacons are dropped, or even modified, those are programmed by the local network operators, by the different enterprises and ISPs that are responsible for administrating the autonomous systems. Moreover, any AS can announce any address range it wants, including ones that it's not actually responsible for. So all of this is based on trust, and motivations may vary. So the internet was designed in a world 4 or 5 decades ago where the parties trusted each other and the motives were to do the right thing. That's no longer the case today. So if you've ever asked yourself who controls the internet, the answer is control is completely distributed. You have all of the different autonomous systems sending beacons, and these beacons are being used for path construction. So here I have a Swiss bank, Zurich. Actually, it's a Swiss Versicherung, Swiss insurance, Zurich. And it's sending beacons out to the internet. And then based on what the autonomous systems do that receive the beacons, that controls how inbound traffic would reach the Zurich autonomous system. So the routers along the path can read and modify data. They can do it in such a way, for example, that the path ends up going over the US, where data is being stored in various data centers, or over Russia, China, North Korea, whatever. Okay, that doesn't sound very good. And you might ask yourself, yes, but again, my Zoom sessions typically work, my mails typically arrive. But if you look globally at what's happening on the internet, you see that things really are working rather poorly. So RENSYS is a global internet observatory that keeps statistics and keeps an eye on what's happening on the internet. So it has observation points throughout the internet, and it can gather statistics from it. So there's some nice data that they have looking at kind of expected versus actual paths that packets take through the internet. So here, for example, somebody in Mexico would like to reach Washington, D.C., and the green path shows what's expected to happen. You go over Texas and Louisiana, but red shows what actually happens. So this is something actually observed. The packet reaches Washington, D.C., but it doesn't get to the end destination. It ends up going over Moscow, Minsk, and Frankfurt. That's kind of strange. Here's another example. From Denver to Denver, if you want to reach from one AS in Denmark to another AS in Denmark, well, typically, believe it or not, you'd actually go over Kansas and Dallas. But what RENSYS observed is the packets via New York were going over Iceland and London. So across the Atlantic twice. Next example, New York to Los Angeles, where the packets should go west, but instead they go east, again over Moscow and Minsk. What's happening in Moscow and Minsk, you might wonder. A final example is if you wish to go from Chicago to Tehran, of course you have to cross the Atlantic here over Frankfurt, but the packets actually cross the Atlantic 3 times, again with a detour over Moscow and Minsk. This doesn't look good, and in practice it really isn't good. Here are some examples of so-called BGP hijacking attacks, where spoofed BGP beacons are sent out to take control over address spaces. A while ago, there was a battle between YouTube and Pakistan, where there's some videos that the Pakistan government wanted taken off of YouTube. YouTube refused, and then the Pakistani Telecom Association, so an ISP, hijacked YouTube's address space by announcing addresses that belong to YouTube. And that went on for some time. Here's another example of a Ukrainian ISP hijacking UK routes, including the UK atomic weapons. In my own country, the Fribourg government, that's a canton in Switzerland, or part of a canton in Switzerland, their address space was stolen by spammers for 3 days, again via BGP hijacking. Cisco has data, they have a data stream you can look online in real time to see all of the different hijacks happening over the world. Sometimes by Moscow, sometimes by Russia, sometimes by France, sometimes just by probably misconfiguration, often by malice. So what's the point? The point is the internet was built using protocols that are interesting, nice ideas, but not more fit for purpose in the world today. So the question then is, as researchers, what can we do about this? We see a problem. Can we make the world a better place? And we've been working on this problem for roughly 10 plus years at ETH Zurich, and also a spin-off company called INRIA that builds commercial versions of our routers and edge devices to build a better internet. So here's some old pictures of this. You can see some of the different people involved. Myself, I'm always the tallest. Peter Müller, who works in programming languages. The two of us are working a lot on verification, some of the protocol design, and Adrian Pereg in network security. And we're also in the picture above. The picture's a bit older. The groups are bigger. We have probably 30, 40 people working at this at ETH, and quite a lot of people at INRIA who are working on these problems. So the idea is to have solutions, but not just write papers, but really make the internet a better place. So the solution is called Scion. Maybe some of you have heard about it. I'm going to, on one slide, explain the essentials of Scion to you. So the world is broken up into, well, first of all, we have autonomous systems, like we have autonomous systems today. And we organize these autonomous systems into something called an isolation domain. So this purple egg, it could be a country like Switzerland. It could be a sector like the finance industry or the utilities industry. And what's important about an isolation domain, why is my animation not working? That is, okay, now it works. Let's do it again. Is that there are some ISPs, they're called core ISPs. For example, for the Swiss isolation domain, they would be Swisscom, Sunrise, some other large ISPs, and they control the roots of trust. An isolation domain doesn't mean that Swiss companies and Swiss end users must only speak within Switzerland. They might want to communicate with America or Russia or whatever, but it means that the roots of trust and control are maintained within the isolation domain. And some of these isolation domains can be closed isolation domains, for example, for finance, where you really need to have permission, which is granted over certificates to join it. Okay, it's a path-based network architecture, so it's all about finding paths and endpoints using these paths. So it's not like the BGP internet, the conventional internet, where you just pick the first hop. You can pick paths. So there's a control plane where paths are discovered, and a data plane where these paths are used to forward packets through the Scion internet. So in the control plane, the way it works is the core ISP send out beacons. So here, if you saw the animation, we had, for example, A and B sending out various beacons. And all of this is cryptographically protected, so the paths are really authentic paths. And the paths are then uploaded by the end ASs onto path servers and stored in caches so they can later be used. Okay, so there's a beaconing phase. And then at the data plane, an endpoint in some autonomous system can collect paths from the relevant path servers to construct a path, for example, from F to S. So the path might be to go up to a core AS, that's this first path here, FDB. Then across the cores, maybe this is a United States autonomous system, isolation domain, over to L, and then a path from a path server here from the American isolation domain down to S, whereby the packet can reach the endpoint. So the endpoints can choose the paths that they want. And packets carry paths. Your packet is not like it is today with a source and destination IP address. Rather, it will contain the path from the source to the destination. And this path is cryptographically protected. So you have transparency and control. You can see where your packets go, and you have guarantees that your packets actually go there. Moreover, it makes routing very simple. Routers are stateless. They don't have routing tables, and they don't have to look up next hops based on address prefixes. Rather, they just have to basically advance pointers through the sequence of hops from one AS to another. So this is a very simple idea at the end of the day, but if you really work out all the details, there's some complexity, but you get a lot for it. So first of all, the core idea in contrast to the internet today is that it's path-based, and endpoints select the paths that they want. You know where your packets are going. And this allows things, for example, geofencing. You saw that if you want to send a packet from Denver to Denver, it could go anywhere. Now you could say it stays in Denver. Now you could say that a Swiss or a Swedish customer connecting to a Swedish bank, the packets stay in Switzerland. Healthcare data stays in Switzerland. You cannot do that with the internet today. You can maybe put a VPN such that things are encrypted end-to-end, but you have no control where the data is actually going, encrypted or plain text, depending on what you're doing. Next is you have fast failover. So you can be multi-homed. You can see all of the paths. If routers on, if links or even autonomous systems go down, or one of your edge devices goes down, you can have very, very fast failover. So you can have millisecond failover. So this is great for business continuity, which is a real problem for industry today. Also, because you have multiple paths and you can see them, you can do true multi-path routing, where you can take data and depending on its characteristics, you can split it up and you can send data along different paths and you have control over those paths. Today, all you can do is pick the first hop. So if you look at things like solutions that attempt to take multiple bad connections and make a good connection out of them, all you can do is control the first hop. You can't control the paths. By design, many types of attacks simply are impossible. For example, BGP hijacking attacks or attacks where your data goes outside of some jurisdiction. And you can also have closed isolation domains where effectively some subpart of the cyan internet is invisible. So here might be an example of path selection and geofencing. You could pick paths from your computer to anywhere in the world based on different criteria, such as when the destination's in Sweden, the packets stay in Sweden, or performance. Or even you could do things like green routing based on energy. Based on how green different ISPs are, you could choose to select paths to prefer green ISPs and to minimize CO2, for example. Here's an example of multipath routing. Between Europe and Southeast Asia, say Singapore, there are generally multiple paths available. The main paths are a high bandwidth path, where when you want to send a lot of data over America, there you have the thickest pipe, so to speak. And for latency, lower latency, you'd go over the Middle East, over the Suez Canal. Although maybe now that's not so good. So there's a high latency, high bandwidth path. That's the western route. And then there's the low latency, low bandwidth path, which is, you can't transmit as much data, but it's a bit quicker. Now with BGP, you have no choice of where your data goes. Traffic follows the cheapest path, which is typically the highest bandwidth path, which is why for video conferencing, for voice, latency is critical. You often have to wait to hear things. So depending on the application, either path might be preferred, and with Cyan, both paths can be offered. So for example, for video conferencing, you could have video, which is less critical but higher bandwidth, going over the US. You could have voice going more directly over the Suez Canal. Okay, so that's Cyan at an incredibly high level, kind of, at 1 kilometer up. But I hope you get the idea. It's a fundamentally very different approach to the internet that's built with security built in from the ground up. At ETH and in the Security Center we have, it's important for us not just to write nice academic papers, but to really get these ideas out. So this work started over a decade ago, And 6-7 years ago, we founded Anapaya Systems, that's this little logo here, to produce an industrial strength version of Cyan. So all of Cyan is open source, but if you want it, with full redundancy and fault tolerance and high performance and things like that, there are commercial systems available that are maintained for enterprises. Our first router came out in 2018. We had successful rollouts in the financial world, so that's the Swiss National Bank, SIX drives, the stock exchange, various academic institutions. I'll say a little bit more about the Secure Swiss Financial Network, which has been up and running since 2022, but the planning started like 5 years ago. And currently in Switzerland, a number of different sectors are moving over to Cyan. For example, the healthcare center. There's something called HIN, the Healthcare Information Sector. 50,000 doctors, hospitals, pharmacies, they're all moving over to Cyan. Okay, how does the Cyan internet look? You have ISPs who are Cyan enabled, which means they have Cyan routers at their edge. All major Swiss ISPs are now Cyan enabled, and there's about a dozen Cyan enabled ISPs in Europe. For example, just as an example, Proximus in Belgium and Luxembourg is Cyan enabled. And we have ISPs in Germany and in France, which are also Cyan enabled. So what that means is that companies which have headquarters and partners and customers, they can communicate over the Cyan internet. They will have Cyan edge devices that will convert IP traffic into Cyan traffic, and then at the edge they can pick the paths they want through the Cyan internet and have all of these properties that I just mentioned. So they can choose paths based on whatever requirements they have: latency, drop rate, jitter, cost, CO2, and they have security guarantees. So again, for the Cyan internet, the Cyan ISPs have to be Cyan enabled with Cyan routers. That's the Cyan core. Then there are these edge devices. You can think of them as security gateways that do a conversion. And there's something else called Cyan Gate, which I won't go into it, but it has applications for IoT or home workers where they can easily make use of the Cyan internet. Because a home worker isn't an autonomous system. They're hooked up to some ISP, but still they can make use of Cyan. I'd like to mention one example of a case where Cyan has really turned out to be very helpful, and this also shows how you can really make a difference in practice, and that's the financial sector. The financial sector is under constant cyber attacks. In Switzerland, finances are important. Switzerland's a banking country, among other things. And what's important for the banks is, on one hand, they can do very efficient clearing, interbank clearing, to settle debts. And on the other hand, things like contact with customers, with point-of-sale terminals, payments, things like that can all be efficiently handled. Communication with their branch offices. And together with the Swiss National Bank and SIX, which controls the Swiss Stock Exchange, we began looking about 5 years ago at bringing this over to Cyan. And started doing this in earnest about 3-4 years ago. Then there was extensive testing. You can imagine if you want to change interbank clearing where billions go over, this is going to be tested to death and pen tested to death and source code reviewed to death. And that happened. And in the second half of 2021, there was a go live. And now financial transactions in Switzerland are going over the public Cyan, over the Cyan internet in Switzerland. Using a particular isolation domain set up for finance. Of course, they tested this to death before using it. We didn't test it, they tested it. This is somebody at a security engineer at SIX, which again runs the stock exchange, where they compared their existing IP network used for interbank clearing. That was a star-shaped network, which would spoken hubs, which would go over the Swiss stock exchange, where all of the banks had one line to the hub, which was SIX, and this was a single point of failure, and it was very slow and it was very inflexible. So they compared with the Secure Swiss Financial Network using Cyan, looking at the failure of a link or looking at the failure of a core router of an edge router at a core ISP, or links failing or edge devices failing, etc. And with Cyan, the fail over time was very, very quick, typically under a second. If your edge device crashed, you'd have to switch over to another edge device that would take a little bit longer. Speaking of things crashing, I didn't even touch anything. Ah, nice. Okay, we should be using. Okay. Whereas with the existing, and sessions would always be upheld, whereas with the existing IP network, failover time was quite long, sometimes many, many minutes, and sessions would be lost, and some kinds of failures were not tolerated because it was hub and spokes, whereas with SIAN, it's ini to ini, it's many to many, where you can use different ISPs, and you can be multi-homed, and you can pick your paths through the SIAN network, and there are many paths. So it was much, much more robust. So we designed this for security, but it turned out to be much more robust in practice. So for just robustness and performance, it was a real win. Now the secure Swiss financial network is up and running. So all financial networks, all banks, and service offices and also financial institutions that work with banks have or are in the process of migrating over to SIAN. Many of them have already moved over. So we have 321 participating institutions, and they're responsible for something real, namely transactions on an order of, on a good day, 403 billion franc per day. So this is something that really, really has to work, and I'm pleased that ideas that came out of research came out of our groups can really make such a difference in something of such value to the Swiss economy and to society. So what was promised and what was delivered, the idea was to replace this old finance IP network with a SIAN network, replace this isolated hub and spokes architecture with something much more robust, and also do so in a way that one can upscale and provide a lot of other higher level services. Once the banks are on SIAN, they can securely commute their remote workers, which was important in COVID and important today, home office. They can support their remote offices. They can have secure communication with their point of sale terminals and the like. And this is working very well. I'll just give you one proof point. At some point I'll have to close before Andrei drags me off. Here, for a prominent Swiss bank, these are their numbers, not our numbers. If you look at how things were before, if you look at attacks with unspecific attempt, this is just people probing. It's not always a real attack. It's maybe just somebody knocking on different ports. Over 2003, over a particular sub-range of time, they had many millions. But moreover, they had many thousands of attacks with malicious attempts, where the packets were really hostile and trying to exploit vulnerabilities in their back-end systems. The same bank, the same autonomous system, when it became part of the Swiss ISD, the financial ISD on SIAN, there were still pings and the like, but these were from internal parties who were just trying to do things like find keep alive, are you still there, things like that. And the number of malicious packets, the number of attacks dropped from tens of thousands to zero. Zero attacks. It's like you're invisible outside of this isolation domain. So aside from high performance, which they're very happy about, and robustness and business continuity, completely free of attacks. Okay, let me try and draw some conclusions. The internet is a very risky place. It's important as researchers that we look at and understand the root causes of this, and it's important as researchers that we work on the root causes. And the good news is, I think that there's a great scope for interaction between theory and practice if we come up with better solutions and we can work together with industry and administrations to test them and develop them and understand the requirements. We can do something to make the world a safer place. If you want to know more, there's this nice book you can read. It's about 700 pages. But you can also look at some of the information in the internet on the SIAN architecture or what Anna Pai is doing. And I also have a course where I cover parts of this that you're welcome to attend. Thank you.
All right, it's my great pleasure to present the next speaker, Elena Pagnin, who is assistant professor at Chalmers with us here in Gothenburg. So Elena is a rising star in the area of cryptography. doing a lot of exciting work on the foundations of cryptography and exciting applications in areas like privacy and authentication. And it's particularly excellent to have Elena here in this forum, organized by Area of Advance ICT, because actually the position that Elena has is an ICT position. So it was a competition of around 130 applicants across all of area of ICT that Elena was part of, and she came on top and got the position at Chalmers within this area of advance. So it's a perfect match, and we look forward to hear about provably secure cryptography.
Okay, thank you, Andrei, from the introduction, and it's very big shoes to fill after Dave's nice talk. I feel very junior now, but I'll try to give you my 2 cents about provably security and why that matters. First of all, being in the beginning of the day, I thought maybe we could agree on what cybersecurity is. So just so that everybody's on the same page, cybersecurity is the process of keeping everything secure, networks, devices, programs, data. We want to keep it safe from damage. And what does it mean usually? That unauthorized people shouldn't access it and shouldn't alter it. Now, how this interplay with cryptography, which is my area of expertise, is that usually cryptographic tools are used in order to enable that. For instance, we saw in Scion, you use cryptographic tools to secure communication and routings. And what is cryptography? Well, it usually looks something like that. And within cryptography, what I work with is data and user authentication. So making sure that you are who you claim to be and the data has not been altered. So what happens when authentication is bypassed? Then people get access to resources, to devices, to networks they shouldn't get access to, and that's very bad. So it's very important that we make sure, are you who you claim to be? Do you have the right credentials before you perform any action? Otherwise, welcome on board. You're free to hijack my system, make my routing packets go wherever in the world. So that's why it's very important. And just to point out research security breaches, I don't know why it's not loading the image, but yeah, there was like some recent news of breaches that happened when like 1 billion of passwords are leaked rather than Russia has entered some data centers in Ukraine and so on. So that happens when somebody gains unauthorized access to things. So what do I do within provable, in particular within cryptography? I do provable security. And what I want to convince you now is that it's an important thing. So what is it? Provable security refers to any type of computer security property that can be proved in a mathematical way. So usually when you use cryptography, you just say, oh, this works, this is good, this is secure, but why so? And the idea is like, I can give you a mathematical reasoning why this is secure. And in particular, when we look at cryptography, what it means is like I can create a link that say, okay, this scheme is secure if you believe in certain definition of security, in certain attacker's model, in certain security assumptions. So there's going to be a bridge between 2 things, and this bridge is going to be a logical bridge. So now it's like, okay, now I'm sure that what I'm implemented is secure as long as the discrete logarithm is hard rather than new post-quantum secure assumptions hold. That's great. Is that enough? Well, we need to make sure to secure all steps. So it's not just about what you're going to implement is actually rock solid from the design perspective. You also need to make sure that your code does not leak information. And we're going to hear more about leakage that happened in side channel attack later on today. So on the one hand, you need to make sure your implementation is rock solid. On the other hand, you need to make sure that what you are implementing has a rock solid design. And on top of that, something that has recently come up within cryptography is universal composability. If my code is, rock solid, my design is bulletproof, still, it might not plug correctly when I want to use it inside a bigger ecosystem. So something I hope to bring to the community today, especially the industry, is like be aware of universal composability. It's important that we can compose cryptographic tools together. And I'm not just saying, oh, this plug has a different ending, so it doesn't go into the socket so well. I'm also saying it might be about the voltage. So sometimes it's like, okay, this cryptographic tool mathematically doesn't match with that one. Okay, let me use another AES rather than a discrete log-based, group-based construction. But sometimes even if it would plug together, you cannot run it in parallel in a secure way. You cannot have speculative executions in a secure way or concurrent executions. This is what universal composability takes care of, and still, we can have, bulletproofs your code, make sure the design is correct, make sure you can plug it wherever and nothing will explode. But what's the weakest link in the chain? Humans. Like, academically, we can do all we can to have proof, to have formal verification of codes, automatic proofs, whatever, but still, we are vulnerable as humans to phishing attack, to social engineering, to choosing weak passwords or reusing passwords, bad security hygienes, and so on. And the way we combat it is, let's have some education about it. That goes throughout everything, both what we can do in provable security, but also like what can you do as a person to avoid this thing, to be aware of social engineering techniques. And this is why I should have used my laptop. Anyway, I want to present a couple of research work of mine so that you know what I'm working on. So this one is not displaying the title, but it's a paper accepted as this year Cryptographers Track RSA conference. And it's about how can I be private as long as I don't misbehave. And when I misbehave, people can remove my privacy. But if one person was able to remove my privacy, no matter what, then who guarantees my privacy? So we want to have accountable privacy revocation. And the way we do it intuitively is like you are sharing your identity among a committee of people. And then if somebody wants to say, okay, the pseudonym has misbehaved, let's remove their identity, then they need to contact this committee, and the contact happens via the blockchain, so there is a public advertisement. I want to remove the privacy of pseudonym 123, and if people agree, yes, 123 has misbehaved, let's remove the pseudonym, then this happens. But this would prevent authorities from abusing their power of removing privacy of people. Said like this seems very simple, but when you go into the details on how you can actually select a committee in a secure way, how can you split your identity among a number of people, making sure for sure this is reconstructible, and you want to do it with provable security, and you want to do it in a universal composable way, so that if this technique was used in a larger ecosystem, things don't explode, it becomes way more involved. And then another paper of mine, which is currently under submission, it's Cascade, so time-based cryptography from space communication delay. And just to give you a pitch of this, here we are looking what happens if we put cryptography on satellites. Now the attack system is completely different because it's very expensive for an attacker to physically go there and tamper with the device, so that's good. We have gigantic distances between satellites, so we can also exploit some delays in the communication. And these delays are predictable because information is traveling more or less at the speed of light, so you know how much time it takes from point A to from point B if these devices are, at the two edges of the Earth or across the horizon of the site. And what we do over there, so my contribution is mostly looking at an ordered multi-signature system. So how can I make sure that all of these satellites are signing some message in a precise order, which goes back to routing. I'm sure that first this satellite talks to that, and then to this, and then to that, and there is no swapping around. So an adversary cannot pretend to be in a different location, and thanks to the laws of physics, the adversary cannot talk faster than light, so certain things are ensured there. If we have this in place, then we can build on top of this randomness beacon, verifiable delay function, and many other cryptographic tools that if we try to build them on Earth, they will be way more expensive to build because on Earth you don't have these distances that you can rely on for time delays, and on Earth usually the attacker is very hands-on and can get a hold of devices and stuff. So that was just a high pitch, and I hope I got you interested into it's important to prove what you use. It's the design is correct. It's important to make sure that the code that you use is correctly implemented in the design. It's important to make sure that when you plug things in, they don't make things explode by different voltage or different socket and plug designs. And it's important that we humans behave in a secure way and don't become the weakest link. And with this, I would like to conclude. I welcome questions, and for more information, you can send me an email or look at my webpage.
Okay, thank you very much.
Okay, welcome back, everybody. My name is David Sands, and it's my pleasure to host today's second session, a session with 3 talks. And I'll begin by introducing the first speaker, and that is Marc Stöttinger. So Marc Stöttinger is professor at RheinMain University of Applied Science. He has extensive experience in embedded system security, in cryptographic engineering, Internet of Things, and has a background from the automotive industry where he worked at Continental with cybersecurity issues. And he's going to tell us today about the intriguing topic of crypto agility.
Okay.
Thank you very much, Marc.
Thank you for the kind introduction. Thank you for giving me the opportunity to contribute to this event. So, in the previous talk, we learned a little bit about cryptography and how to prove that the cryptography under certain assumptions are correct. What I'm going to go now in this talk is looking from the engineering perspective. So how I can use actually cryptography, or what I should be conscious about if I'm using cryptography in a system, and what should I do if I need to change my cryptography. So what are the odds and what I need to consider. So therefore, first I want to give a motivation. After that, I will come to the topic of crypto agility, what it is actually, and then the impact on cybersecurity with respect to crypto agility, and then I will draw a conclusion. So cryptography is nowadays almost everywhere. I just give the example of the automotive domain because I've been working there for quite a while. And in previous work, we investigated actually how to exchange cryptography in a device or in an automotive vehicle because of post-quantum cryptography. I will come to that later on. But as you see, either for example, electrical charging, which comes now a new challenge, not only from the infrastructure perspective, but also how to secure it, how to make it repudiation, how to ensure non-repudiation, that you're actually charging your vehicle. Also, you will get more and more microservices over time with vehicles. Like you have extra service in the vehicle you can purge, you can pay, for example. This will come up in the future. What's already here, already there nowadays is so-called feature activation, which means you can, let's say, rent some features in a car which are usually not existing. So the biggest sales pitch back when I was Continental was the, let's say, Christmas horsepower. So you can buy additional horsepower to have more horsepower for your car over Christmas time. If it's worth, I don't know, but this was the selling pitch. Then you have other things like access delegation. So you can then pass on a key, for example, in order to put some package delivery in your car, for instance. And of course, you need to maintain security of a car. And since cars are getting more and more software-centric, software updates are very important to secure. So just give you an idea why it's worth to think about how to deal with cryptography from a, let's say, technical perspective. However, last year at the G7 leader committee, there was a statement that Europe needs to be more resilient in terms of cyber defenses, also investigating into, they call it quantum resilient cryptography standards, which means, Elena already gave a short introduction about when we have quantum computers to a certain extent, that other attacks are possible, and some cryptographic schemes doesn't hold anymore. So this is interesting because now it becomes on a political level acknowledged, which means there's now momentum also for industry to apply to it maybe. And a little bit earlier, before this official statement came, the German Institute of Information Security gave this announcement saying, okay, future products should have cryptographic agility in mind, in perspective of quantum computers. So having this notion in mind that the existing asymmetric cryptography might not hold, in the existence of large-scale quantum computers, you need some means to adapt. And what does it mean, quantum resilient cryptography? There are now two, let's say, big classes you can separate this word quantum cryptography into, which stands for some kind of resilient against attacks with large-scale quantum computers, which are not existing at the moment. But due to certain insights, a lot of researchers believe that in 20 years, it should be possible that some entities could have access to it. Yeah? So, and the first thing is you can go for so-called quantum cryptography. I put it in quotation marks because if you look at it, it's more like an exchange of symmetric keys by using quantum mechanics. So this is what you see nowadays when a lot of physicians try to entangle with light sources a common action with the 2 points and then transfer symmetric key and can prove that nobody listens to it. Yeah? But this only involves transferring keys. So a very famous protocol for that is the BB84 protocol, for instance. The other class is post-quantum cryptography, where Elena was also touching a little bit. So the major difference is that the first one uses new technology, quantum technology. Post-quantum cryptography runs on classic computers, but post-quantum cryptography uses mathematical problems, which seems to be resilient even in case you have the opportunity to run something like Schnorr algorithm or Grover's algorithm, which are used to have an efficient way of breaking the discrete log algorithm, or in a way of efficiently sorting, for example, values, which you need to break symmetric crypto. And this major field was driven or started in 2016 by NIST, and NIST said, so National Institute of Standardization Technology in the US, and they said, okay, we need new algorithms. And now they just announced, like half year ago, some standards. So we have now in the standard dilithium, Kyber, which are lattice-based, Sphinx, which is hash-based, and Falcon we have also as lattice-based. In addition, we have XMSS and LMS, which are not standardized or not going to standardized by NIST, but by the IETF, and NIST acknowledged them that they are also good to use. And there are even more algorithms to come, which are currently under evaluation. So this means we have new algorithms, but if you want to use it, we want to make sure that they are correctly implemented. What Elena said, we need to prove that the implementation is correct. And this comes with a word of high insurance cryptography, so that your implementation is secure and correct. And in addition, when you think about crypto agility, I will come to this point later on, you also need some means to tailor your cryptographic primitives to your application, because the new algorithms are not that diverse anymore like RSA or ECC. And then also you need to consider maintenance of these algorithms. So, which means one can think crypto agility is just replacing one algorithm by another. No. It's more process which takes longer time, because we already had this problem of mitigation of cryptography, and it's repeating. So who of you knows DES? Who of you work in the banking sector knows DES? Okay, you know? So you know the pain between DES and AES, which are just symmetric crypto, but we have also the pain with SHA-1 and SHA-2 transition, and now at SHA-2 to SHA-3 transition. So it seems like this crypto agility is actually an old problem, which is now getting promoted by finding new quantum computer resilient asymmetric cryptography. That's just one point, because it's not just replacement. The other is that, I said already, the new algorithms, for example, like Kyber, you can use for encrypt messages with asymmetric crypto, but you cannot use for signature schemes. In the past, you could use ECC or RSA to do both. This is not possible anymore, which means your architecture, security architecture changes. You need to think about, okay, what kind of algorithm I need to put, what kind of security goals I need to fulfill. And there are also other side effects with other algorithms. I will not go in detail to that, but you cannot just plug and play it because you have different, let's say, properties to the algorithms. You need to fulfill that you're actually using them correctly. This touches actually to the ground what Elena said before, that humans could be weak link as well. The next point is you cannot just plug and play it. You need a transition phase, because when you're in industry, you have a development or pre-development, and then comes to production, and then to industrialization, which means it's not a hard switch to switch. You need to prepare it in order to put in the right cryptography at the transition phase. Also with NIST, when they just start the announcement before they start the announcement of the standards, they had a very long competition to evaluate if the algorithms are strong enough or not, and up to now it's still questionable for some candidates if they are really strong as the knowledge we have from them is fulfilling at the moment. And the last point is, even so you update an application, you need also to consider the impact of the ecosystem. Just thinking about you have a car key which you want to update now to asymmetric crypto. It's not just a car key you update with a new algorithm. You need to change the key management scheme. If you're a tier 1 or tier 2, which provide to an M, you need also to change the communication between them as well. So the entire ecosystem is affected, meaning you also need to consider about policies where we come to operational and security perspective issue. So, but the question is, crypto agility seems a mean to exchange algorithms or cryptographic algorithms, which are some kind of foundation for a lot of security measures. But the difficulty at the moment is that there's no clear definition at the moment in academia and industry. So it's actually an ongoing research field. 4 weeks ago, there was a community founding which are especially looking only how to realize crypto agility and what are the definitions of crypto agility. So we had in this meeting, for example, EBM setting, where put a lot of thought into it, what is needed in order to perform agility in a secure sense with means to cryptography. And they come up with a model which has certain points. So they first say, okay, the algorithm itself needs to be agile to exchange. The protocol should also fit. And the implementation should also give some means for interfaces to exchange different algorithms. But even on top, you should also be able to change the security strengths. So simple example would be in symmetric world going from 128 to 256 bit for security. Sounds easy, but if you're in a mass production environment, every bit counts you have for memory. Yeah? So sometimes you do not have 128-bit additional memory space to store your larger key. So it becomes difficult as well. And then they say, okay, the migration process itself should be also agile, meaning that you have different means to migrate to a different point. So Fraunhofer has a different model. Fraunhofer is a research institute in Germany, and they said, okay, it's much more important to have knowledge about the system itself before you mitigate. And this is a big difference between them. And on top, with all this transition to post-quantum cryptography, there's also now guidelines from official institutions, but even those official guidelines are not aligned internationally, so this becomes quite diverse and difficult for an international player. So some say go for hybrid schemes. We heard from David talk a little bit from the last question. They please directly mitigate. And the other idea now is, in order to say how good you can mitigate, is to have something like a maturity model, to say, okay, how well you can actually change your cryptographic scheme to another scheme. So, giving you a rough idea about crypto agility, what are the challenges that will come? The biggest challenge is you have a broad ecosystem and you oversee some algorithms. You still have some RSA or ECC in the library, and quantum computer exists, so you're still using weak or outdated cryptography. The other one is your transition to updated cryptography is delayed because you're not having all the information at place and all the processes. Then you can also have improper implementation of the algorithms and protocols because they're just standardized, how to check it. This will be something for high assurance code and composable security. And the other one is, the last point I would like to touch is the incompatibility and the architecture and design perspective. But there are ways to circumvent this. So in order to avoid outdated crypto, you should have a cryptographic inventory where you have a list of what kind of algorithms you're using in your products. Then you should use a crypto agility maturity model to see how you need to you trim your process and how far you are actually or able to transmit. And for the improper implementations, high assurance cryptography and composable security are the means to circumvent this. And for the architecture, you should consider crypto agility in all phases of the product lifecycle, meaning if you want to edit crypto agility, you need to put it in the design phase, yeah? Meaning most likely you have technical interface to exchange algorithms, but then you also need to assure that it's used correctly later on when it's in the field. You should add some kind of policies to it, yeah? That you use it correctly. For example, XMSS is a stateful hash signature scheme, which means only one instant is allowed for signing at a time. So, and putting it into a life cycle perspective, you actually need to extend this approach about policies, changing from state to state. Meaning, when you are in the field, you should have some additional means in order to run operational security measures. For example, if there's an attack or a weakness comes up, you need to maybe exchange the algorithm. What does it mean from a security perspective, architecture perspective? Do you want to allow remote software updates, or you say, okay, I need physical access to the device in order to avoid that with a broken algorithm, somebody can actually update some software remotely. Yeah. So in a sense, I see the topic of post-quantum cryptography actually promoting an old question, which is cryptography, how to exchange cryptographic algorithms from an engineering perspective. We need tools which are currently getting developed, and we need also maturity models to know from the process perspective where we are standing. And the last point I want to highlight here is that every phase in the secure product lifecycle should be considered, meaning from the design phase, over testing, and when it's in the field, even when it's when it's taken out of the field. And with this, I would like to conclude my talk. So I gave multiple references. You have here the reference for later on for reading, and I'm now open for question. Thank you.
Thank you very much. So I welcome to the stage our next speaker, and that's Simone Fischer-Hübner. Simone is a professor at Karlstad University, and we're also very proud to say that she is affiliated professor and currently visiting professor at Chalmers. In the area of IT security, Simone is very well known to those of you that have studied security. She, over 20 years ago, founded the Swedish network for PhD students in IT security, something that has been very important for our Swedish security researchers. She is head of the PRISEC group, the Privacy and Security group at Karlstad, has an extensive track record, not only in security, but above all, in privacy-enhancing technologies. And today she's going to tell us a little bit about usable access permissions. Simone, thank you.
Yes, thank you very much. I'm very happy to be here. Yeah, honored that I have been invited, and I will present work that is also work in progress that we conduct here at Chalmers partly, and I will also point to work that is also later presented in the poster session by my colleagues, so which complement my presentation. So I will talk about usable access permission management, and my colleague Elena already pointed out that the humans are the weakest link, and indeed most security incidents are actually due to human errors, like different reports constantly show, like the very soon 23 data breach investigation report has shown that 74% of all security breaches include the human element, with people being involved either with error, privilege, misuse, use stolen credentials, social engineering. So we see that human factors related to access permission management is very important, especially also during the pandemics. This has evolved because then we had a push for digitalization, and here it was also shown by Elisa that the most frequently occurring issues are due to human errors and also system misconfigurations. So we have to address usability issues for the end users, but also for system admins that are configuring systems. And there are a lot of usability challenges around this that have already been researched for several years that explain why usability and the human factors are such a hard problem. And actually, I would claim that we have a lot of nice security and privacy solutions, but it is very hard to make them usable, understandable, and successfully deployed in the end. So usability challenges for lay users are mainly due to that security and privacy are actually only secondary goals for users. This was already researched in 1999 in the famous paper Why Johnny Can't Encrypt in the context of PGP. So users typically have another primary goal. They want to look for information in the internet or configure or to make a purchase on the internet, and in this context I do not want to be disturbed by security warnings or privacy policies or cookie banners, so usually users quickly click it away without really paying attention and understanding what they are doing, because security privacy is not what they want to spend their time on. It's only a secondary goal. And then there's also no one size fits all. So we need different types of configurations of access control permissions for different type of users that matches their preferences. So users have different preferences. Usually you can also find typical privacy personas, but they differ also between different cultures. For instance, I originally come from Germany. Germany is a risk or uncertainty avoidance country, according to sociologist Hofstede, while Sweden is much more, Swedes are much more ready to take risks. So for Germans, transparency and control would be much more important than for the average Swedish users. Similar distinctions can also be made for male and female users. There are also some distinctions. Usually we saw in a study that males, for instance, would rather trade usability on cost of control, whereas females would rather like to have privacy controls on the cost of usability. So we need different types of configurations for different type of users. Yes, then we have the system admins that are security experts, often or usually, and they of course have privacy or security as a main goal. However, they also have to deal with complex trade-offs that need to be made between different security and privacy protection goals, which can be quite tricky. For instance, the trade-off between data minimization and transparency. And for instance, for machine learning model, you can protect personal data in machine learning models with differential privacy, but this goes on cost, can go on cost of the explainability of the machine learning model or fairness and utility. So you have to find suitable trade-offs, which is also not easy and straightforward, and also multidisciplinary expertise is needed for this, not only purely technical expertise. And this we have, for instance, also experienced. I come first to a short user study we did in the Prisma Cloud project, which was a Horizon project on privacy preserving crypto for the cloud, where we used, used secret sharing for secure archiving in the cloud, which has the advantage that it is keyless protection. You do not have to manage keys, which is more usable, but you have to rely on the so-called non-collision assumption, because with secret key sharing, you can split a secret like a secret file in different shares and n shares. And you need at least k out of the n shares to reconstruct the secret, while if you have less than k shares, it is impossible, or it should be impossible to derive anything. There are schemes that are informations by Shamir, secret sharing. It is information theoretically impossible to derive anything with 1 or with less than k shares. So you can split a secret and a secret file into different shares and store them at different cloud servers. And you do not rely on key management, but you have to rely that less than k servers are corrupt and might collude against you. So there are some pros and cons. Now the question how to configure it. The technical solution is quite easy, but the challenge was really how to help system admins to configure this securely. And here we did the studies with interviews and later expert evaluation. It also showed that you do not only need technical expertise, how to pick the parameters k and n and what type of cloud services. You also need legal expertise or understanding that a secret share, even so from one single share you cannot derive any information, still it constitutes, according to the GDPR, pseudonymous data, because you can still re-identify it with other shares, and thus it's still personal data. And then you have to know there are restrictions, and especially after the Schrems II European Court decision, on where you are allowed to store the data, where you are allowed to use non-European servers and so on, so it's quite tricky. Also organization requirements in terms of costs, procurements, data processing agreements need to be considered. And then you have also security privacy trade-offs, so you could use secret sharing for achieving better availability through redundancy, but it could be also used for confidentiality, privacy. So it depends for what goals you are using it. And we then came in the end up with solutions which where we had pre-settings for configuration based on the data type. So we instead of the protection goal, because that was also challenging for system admins to rank protection goals. So for instance, if you had high confidentiality requirements, this applies for special categories of data according to the GDPR, or business secrets or security classified data. And then there would be a pre-setting that you should have more than standard secret sharing, or you should also configure it with, for instance, a k that is not too small, because then more people need to collide against you. But the number n should not be too high, because then you have more potential attackers. At least 2 of the shares should be preferably on the private cloud servers, and at least in Europe, so that non-European cloud services could not attack it together. There should be data processing agreements, procurements, and in addition, for very sensitive data, it should additionally be encrypted. Then you lose the advantages of that you need key management, but still, in this case, it would be required. So, but conclusion, it was not so easy, and it requires also multidisciplinary understanding. So now we come to the end users and how to enhance security here. And here we also wanted to check how much we can use semi-automation and pre-settings to enable more usable solutions. And here in our VAS project, together with my colleague Victor Morel, we first classified the field, what are what are privacy decisions that could be automated and to what degree they could be automated, what solutions exist. So we can have privacy permissions, so access control settings. There can be also privacy preferences like do not track or please repeat, where it's only wishes, what the users would like to have. Then we have consent as a decision and reject, which is revoke consent, object, do not give consent. And we look to different solutions and also how far these are GDPR compliant. So there are nice solutions that evolved in the last 8 years of so-called privacy assistants that use machine learning to predict the privacy preferences and wished privacy permissions of users with more than 95% exactness that you really match the user preferences. However, there are also legal issues with fully automating permissions, preference, consent. For consent, you always need an affirmative action, so it cannot be fully automated. And also for privacy permission and preferences, if they are set automatically for the user, then also this would not be in line with the requirement for data protection by default by the GDPR, because you should have the most privacy-friendly setting by default. So semi-automation is a way, but semi-automating nudging for privacy preference, for privacy permission is also an approach, can also be discussed under ethical questions. How far is nudging ethical? So we work in our VAS project on how this could be, how users could be asked to change their permissions with dynamic consent and machine learning supported on-the-fly permission management for IoT tabs, trigger action platforms. So IoT trigger action platforms in the context of Internet of Things allow users to customize their smart environments by creating IoT apps with automation rules that trigger action based on specific events or conditions. And the problem, different security problems were nicely elaborated by my colleagues, including Andrei, which also showed the problem that trigger action platforms like the IFT platform only provide coarse-grained access control. So trigger action platforms, they enable to link different services. You have a service platform that triggers an action. For instance, if you take a photo on your own Android phone and then automatically the data could be updated in Dropbox. So different service sites are connected. Like here, the user's Android system is with Dropbox via the IoT platform. And the problem is that fine-grained access control is not enabled. So a need was also identified for fine-grained access control and bundling and automatically deriving user-level permissions. And for this, we did now in our project different studies. First, for doing a user segmentation to find out what are typical privacy personas that reflect typical privacy preference settings that users would like to choose. For this, we had scenario-based focus group for deriving privacy factors that matter for the users, preferences and concerns, based on scenarios like this one. If someone catches a new video with a smart or her smart glasses, it will be automatically uploaded to TikTok, and then and then we found out factors that also differed from the traditional internet. For instance, that users would like to have transparency before final actions, control, trust in the third-party service providers. So a lot of requirements also regarding to the third-party service providers that trigger actions. And the next step is to do a user survey, an expert evaluation, and a triangulation for finding suitable user segmentation. So please visit the poster by my colleague Piero Romare on this topic. And here my last slide, another ongoing line of work is that we try to enable situations where users can be asked for changing their permissions on the fly in the context of dynamic consent. So the idea is the users start with a privacy by default setting, or they can choose, select privacy profiles that we have derived through our segmentation at the start. And later, while they are operating, they can manage the access permissions on the fly before, without being burdened with extra actions. So on instances when they are anyhow asked to make access decisions, they are asked also whether they want to adapt their settings non-intrusively. So for instance, if there's an access request and no access permission is given, there will be a request for consent. Then the users will be asked whether they would like to give consent. If yes, only for this triggered actions, or possibly for also in future for all triggered actions for this service provider and purpose. And then their preference settings can be adapted. It can be also mentioned that this option matches their privacy preferences. That is monitored locally with the help of machine learning. And then the adaptation is done. In the other case, if the access permission is set, but it is detected that the action is anyhow risky because it deploys sensitive data, special categories of data, third country transfers or profiling or repurposing, then also dynamic consent should be requested according to the GDPR. For instance, if location data suddenly gets sensitive, someone visits a cancer clinic or abortion clinics, then the data or the location gets very sensitive. Dynamic consent should be requested, and here we do a similar thing, so that the access permission should be adapted on the fly to the stricter settings. At least the user has the option. Yeah, this is basically takeaways, and I can also conclude, that there are different challenges remaining for finding suitable trade-off settings, ethical, GDPR compliant, matching user preferences. And it gets even more complex with the AI Act. I just also discussed, we have not only security privacy trade-offs, but also in future with the AI Act, trade-offs with sustainability, environment, social, societal security and so on, also with the Digital Services Act. So it will get even more complex. Sorry if I talk too long.
Thank you very much. Thank you.
So please visit the posters by Victor and by Piero.
Say again.
Please, if you want to know more, you can also visit the posters by Victor and Piero that work with me on the second part.
And that brings us to our final, last but not least, speaker of this session. And it's our keynote speaker for this session. So it's my pleasure to introduce Pontus Johansson. Pontus is professor at KTH, Stockholm. He is director of the Center for Cyber Defense and Information Security. He has a broad and extensive interest and experience in cybersecurity and computer networks. And he's also a member of the Royal Academy of Engineering Sciences. And I believe that rumor has it that you are among the top 50 most important people in tech, according to a recent poll in Sweden. We're very happy to have you here with us today. And you're going to give us a slightly broader perspective on the role of research and innovation in cybersecurity. So I'm looking very much forward to your talk. The floor is yours.
Thank you. It's very nice to be here. Yes, I would like to give a bit of a broader, argument for the importance of research and innovation in cybersecurity. I think it's more important than most people think and what you would see in the news, for instance. I thought I'd start with an example. These three guys are Niv, Shalev, and Omri. They're the founders of the NSO Group. And the NSO Group is a company in Israel that is now very well known for having developed the Pegasus spyware. So this is a piece of software that can be surreptitiously installed on cell phones in order to spy on people. If you have Pegasus on your phone, you typically don't know it, and the attacker will be able to watch you through your video camera, listen to the microphone, read your emails, access all your data. Whatever you can do, they can do, and more. And the Pegasus has been the software. We've seen it in many different incidents. There have been a lot of reports about people who have been targeted. And the SO groups, they claim that they only sell to well-meaning nation states, but it turns out that Pegasus has been found on the cell phones of journalists and human rights activists and lawyers and academics and all kinds of people. Heads of state have been targeted. Emmanuel Macron was on a list for targeting. Also other heads of state. I think the most gruesome target was Jamal Khashoggi. You might know, was a journalist from Saudi Arabia who was targeted by the Saudi Arabian government through NSO and the Pegasus spyware, and subsequently lured into the Saudi Arabian embassy in Turkey and killed. So we don't want this to happen. So, of course, the big tech companies like Apple and Google and cell phone manufacturers, they spend a lot of effort trying to prevent these kinds of attacks. But it's very difficult. So one of the attacks, one of the exploits that was used by the NSO group against the iPhone is called forced entry. I thought I'd just go through with you this attack. It's pretty interesting. So if you have an iPhone, there's this iMessage application where you send text messages to your friends. You can send pictures, and pictures can be of the format GIF. And at some point, Apple, they wanted, if you send a GIF can be like a small movie. And if you want Apple wanted these movies to loop endlessly, so they made some changes to their code, and those changes introduced this vulnerability. So it's a really, small thing. It's a small piece of functionality. You really don't need to loop endlessly your GIFs, but that can introduce a vulnerability, such a thing. So the NSO group, they found that there was vulnerable code in a part of the iMessage system that they first had to reach. It was kind of hidden deep down among all the code in the iMessage application. So what they did was they devised a GIF which could be sent to the target. You can see it here, bad.gif. It was sent to iMessage. It sends to iMessage, and iMessage checks the file extension. If the file extension is .gif, then it will pass this file onto IMGIFutils, which is a library, in order in this case, just to copy the GIF from one place to another. IMGIFutils uses Core Graphics, which is an Apple library also. Core Graphics looks not at the file extension, but it looks inside of the file and looks at what kind of file it is. And so here, the NSO group, they were clever. So they had inside of this GIF, it wasn't really a GIF. It was just called .gif, but it was a PDF. That allowed them to trick the Core Graphics library to send it to the Core Graphics PDF decoder. And the Core Graphics PDF decoder looked inside of the PDF, and it found a file format that's called JBIG2. And JBIG2 is an arcane file format. It's super old. It's from the 90s. It was used to compress images for copying machines. So there's no need for iMessage to have this piece of code. But it's there because at some point it made sense. and it costs some effort just to remove things. So the JBig2 format, if Core Graphics sees that this is JBig2 format, then it will invoke the XPDF JBig2 parser. And this was where the vulnerable code was. So NSO Group, they went through all these difficulties just to reach the vulnerable code. And that piece of code looks like this. You don't have to understand all of this, but you can see that there's this integer. It's called numsys. That integer is used to allocate a piece of memory in on the phone. So the memory is just as big as numsys is. It's on the second highlighted line here, the allocation of the memory. And then the code will place a piece of data into that memory. The symbol dict here. But the thing is that integers, they have a finite size. So what can happen, just like with a clock, when it reaches 12, you run back to 1. So it's the same with the integers. You reach a sufficiently high number, and it's going to reset to 0 and start from there. It's called an integer overflow. And the NSO Group, they discovered that they could, by passing a really large object into a very much larger than the developer of this program ever thought about, they would be able to overflow the integer. And if you overflow this integer, then numsys here becomes small, but the data is still large. And so what you end up with is a situation where you have a buffer now allocated for the data that's too small, and then you have data that's large. And then what you achieve is a buffer overrun. So this data that is beyond the buffer, it ends up somewhere on the heap here in this data. And if you're really good, like the NSO hackers are super good, then you can groom the heap, it's called. You can do all kinds of things to curate the data so that what you write over the buffer boundaries, that it ends up exactly where you want it. And you can, for instance, change where pointers are pointing. So this data here below, if you groom correctly, it's important data, and it can allow then, if you can affect a pointer, that means that you can now control the flow of the execution of the program. And as soon as you do that, you're in a very good position to take over the program execution and run your own code. If you run your own code on an iPhone, well, then it's game over for the target. So this was the vulnerability, and there are many vulnerabilities like these in our software systems today. If you want to fix this, all you have to do is, which they did when they found out that this was the problem, after people had been targeted, after this had been used, they fixed it by a single line. An if statement says if it's too big, then reject it. Don't accept enormous pieces of data. That was the fix. Very simple. So this is an example, and I'm thinking, what is the root problem here? Because we see these kinds of problems all the time. All the time. Thousands and thousands and thousands of similar vulnerabilities. What's the root problem here? And I would say that in this case, the root problem is Derek Noonberg. Derek Noonberg is the guy who developed the XPDF parser library. And that's an open source library that's used by Apple. There's lots of open source out there, and lots of it is used in commercial products. So Derek Noonberg is just a guy. He likes to play drums. He built his own homemade cider press. Actually, he's not just a guy, he used to be a grad student at Carnegie Mellon University. He wrote a paper actually in the 90s about the discovery of bugs in software. So he's more than just a guy. He's not just any programmer. He's usually security conscious, given this paper. programmer. Nevertheless, he made this mistake. And so the thing with Derek is that he needs to know so very many things. So he needs to know all about C++, which the programming language here is. He needs to know about the platforms on top of which his program is executing. He needs, of course, to know about PDFs, the file format, how does that work? He even needs to know about the JBig2 format, this arcane format from the 90s. And then, of course, he needs to remember, he's been developing this since the 90s, he needs to remember the 100,000 plus lines of code that he's written in this library. He needs to know that also. And if he doesn't want to make these kinds of vulnerabilities, create these kinds of vulnerabilities, he needs to know all about integer overflows also. And then in the background here, you can see a list of all the other kinds of vulnerabilities that you could happen to introduce into your C++ code. He needs to know about all that also. And then he's not allowed to make any mistakes. Maybe he knew about integer overflows. I think maybe he did. But it's super easy to forget these things. So Derek is just one out of tens of thousands, I guess hundreds of thousands of people who have contributed code to an iPhone. All these people need to know all this stuff. And of course, that is a very, very high bar to set for software developers. So this is one example of what I'm going to get to, which is the issue of cognitive complexity. Another example is, the Linux system. There's the Linux kernel. That's like just like it sounds. It's the kernel of the Linux operating system. Linux is everywhere on the internet, everywhere in our many of our cell phones, in the Internet of Things, on servers. The cloud is, just a big Linux cloud. So Linux is completely crucial for everything, for our complete digital infrastructure. And in Linux, they have bugs. They're typically, most of them are just harmless bugs. They have something like 10,000 bugs in a bug tracker. And as you know, surely Linux is an open source project, so anyone can contribute. So what you can do if you want to is you can contribute to fixing one of these bugs. You look at the bug, you understand what the problem is, you write a patch for it or some new code that fixes this bug, and then you send it over to the Linux maintainers. And they look at your code, and then they say, okay, this looks good, thank you very much. We'll introduce this into the Linux, next version of the Linux kernel. So there were some researchers not so long ago, a couple of years ago, who wrote a paper which is called On the Feasibility of Stealthily Introducing Vulnerabilities in Open Source Software via so-called hypocrite commits. So what they did was they created these fixes for bugs in the Linux kernel code. But when they fixed something, they also intentionally introduced a much more harmful vulnerability. And then they checked if the Linux maintainers would notice that they'd introduced these vulnerabilities. And these were very serious vulnerabilities. There were use after free vulnerabilities, point to memory corruption stuff, just similar to the one that I showed you here. And you can see from this table here that there's the catch rate. So for instance, concurrency issues, these are problems when two pieces of the software kind of talking simultaneously that can create vulnerabilities. The Linux maintainers, they discovered a fifth of the vulnerabilities that had these or the patches with these vulnerabilities in them. Just a fifth. And you can see the numbers here for other kinds of vulnerabilities also. So if you want to be completely sure that you have introduced the vulnerability in the Linux kernel, you submit 3 fixes. And you can be very certain that you're going to be, that one of them, those vulnerabilities is going to be introduced in the Linux kernel. This is very scary, I think. And here, we'll also return to the issue of cognitive complexity. The problem here is that the Linux maintainers, good people, but it's impossible for them to find these vulnerabilities because it's very, very hard. It can be, in this paper, they had vulnerabilities where they found that there were preconditions. There were already 2 kind of seeds for a vulnerability in somewhere in the code base. And the Linux kernel is like 50 million lines of code. So they found that for use after free, for instance, there was this one thing here, there's this one thing here, and then they introduce the 3rd thing here that opens up this vulnerability and makes it exploitable. It's very, very hard to find these things. So these are 2 examples. But the thing is, if you look at, here on the left, you have Microsoft's monthly security update. Every month, this is like 1.5 years old, that's for April last year. But it looks the same every year, every month. Every month, Microsoft discovers that they have 100 new vulnerabilities in their products. They're equally surprised every month. 100 new vulnerabilities this month too. And the next month, and the next. It's been going on like this for decades. They just can't get rid of all these vulnerabilities that just keep. It's like they have a production apparatus inside of Microsoft for just producing these vulnerabilities. And like, there's a dozen of them every month that are critical. Remote code executions, pretty much like the one I explained here, that you can take over a machine from the internet. And the thing is, Microsoft is good at this. They're good at software security. Most companies and developers are much worse than Microsoft are. And as Simone talked about, the problem is not just developers, the problem is also system administrators. So on the right-hand side, we have the US Department of Defense. They have a bug bounty program. If any American citizen, I think they limit it to, can search for vulnerabilities, try to hack the web sites of the United States Department of the Defense. They found, I think it's something like 25. Here it says 20,000 vulnerabilities. So they've gotten 20,000 vulnerability reports from people on their web-facing systems. That's a lot of vulnerabilities. That's even more than Microsoft's 120. This is since 2016 when they launched this bug bounty program. And they're also often very serious, like unauthorized access to personally identifiable information leads to mass account takeover. These kinds of vulnerabilities are common. And the United States Department of Defense, and Microsoft, they care about security. It's not that they don't care. They also have resources and they have competent people. So what's the problem? Well, as I have alluded to, the problem, I believe, is cognitive complexity. And this also is in line with what Simone talked about. It's very, very difficult for people who are system administrators, developers, users, to do the right thing. In particular, if you're a developer, system administrator, it's the issue of cognitive complexity that it's just the problem is too hard. The code that you're working on is too big. It doesn't fit inside. You know, our heads, they're not so big. The problems that we ask these people to solve for us, they're very, very big. So we have 2 ways that we can go here. Either we reduce the systems that we use to the size where we can understand them. But that means that we're going to reduce them enormously. If you really want to be sure that you are reasonably sure, say, that the system is secure, you can have an operating system that's 50,000 lines of code. I think that's pretty much the biggest that has been formally verified, which is a pretty good standard. Linux kernel is 50 million lines of code, so you can't have the Linux system. It means that everything that you know about computing has to go. So that's one way. We just reduce the systems, but we're not going to do that. So instead, I think there's only one other way, and that is to build better tools for these developers so that they can build secure systems. We're asking these, this is like asking construction workers to build a skyscraper with a shovel and a hammer. It's not going to be a good skyscraper. And it's the same thing with the tools that we have. If you have C++ and you're writing a PDF parsing library, you're going to run into problems because the tools aren't good. So we need new programming languages, we need new operating systems and new development environments, analysis tools so that we can find vulnerabilities, verification tools. We need lots of this stuff. And so this is where my argument then is that the way that we develop these is through research and innovation. This is the way that we generate these tools. So I think that cybersecurity problem, it cannot be solved unless in any other way than through research and innovation. Now in the meantime, of course, because that's going to take decades probably, and in the meantime we're going to have to live with all these vulnerable systems that we have. It's going to be like on this picture here, there's this leaking wall, and we're going to need lots and lots of people to plug the holes. So there's this big cybersecurity workforce gap. There are too few people in the industry. We need much more people. So we have, according to a study here, there's 4.5 million people working in cybersecurity in the world. We need 8 million people, so there's a gap of 3.5. And this gap is growing. Even though the workforce is growing year by year, the gap is growing faster. So we really, really need to educate a lot of people also. So research, innovation, and education. And the thing is, all of these things, that's why you are here at Chalmers, because Chalmers happens to offer all of these things. The university sector does that, together, of course, with other parts of society involved in these activities of research, innovation, and education. One of those initiatives that I'd just like to spend a few minutes on is a very recent initiative here in Sweden that we call Cyber Campus Sweden. And the idea with Cyber Campus Sweden is to create a common collaboration place for research, innovation, and education. So we have today good universities, we have good vocational universities, yrkeshögskolor. We have companies involved in cybersecurity, of course, doing research also, innovation, and government agencies. But we're not collaborating as much as we should, and we're not doing as much as we should. So the main idea of Cyber Campus Sweden is to create this national center where there will be many partners. And we've been arguing, Simone, for instance, and I have been arguing for this for a couple of years. Now, just a month ago, we got an announcement from the government, from the Minister of Education and the Minister of Defense, that the government will now fund Cyber Campus. So it's going to happen now. So after the turn, by New Year, we're going to be able to inaugurate Cyber Campus Sweden. So what we're going to do there is we're going to offer, for instance, lifelong learning in a better way than the universities have been able to do so far. The universities really haven't been able to meet the challenge of educating people who are not in these big 5-year engineering programs, for instance, like at KTH. Also, universities have not so far been very agile. There are many courses that we should be offering that we don't offer. We don't have courses in cloud security in Sweden, as far as I know. We don't have courses in SCADA security, in threat intelligence. There are many topics that I believe that we don't have courses in Sweden. At least not offered by the universities. And so more agility is something that we're also hoping that we can achieve through Cyber Campus. But not only education, Yeah, actually, another thing on education is that at KTH, we have a lot of people doing cybersecurity and a lot of courses in cybersecurity, but we don't have any course in forensics. And forensics is a really important topic area. In Halmstad, all they do is forensics, but we don't collaborate. So our students, they don't learn anything about forensics. And in Halmstad, there are many things they don't learn that KTH could contribute with. So we could collaborate much more when it comes to cybersecurity education. When it comes to research, we have in Sweden small research groups, and infrastructure is a problem. If you're my group, for instance, we've been wanting to procure a car to do some car hacking. Now I'm in Gothenburg, so I guess this is the Mecca, but we also want to do that in Stockholm. But just for our small group to buy a car, it's a lot of hassle, and we don't have people who do that. So we have to ask our postdocs or people who are in our group to, could you stop doing research and instead go buy a car? And you're going to have to go through this whole procurement process with KTH and government procurement. You're going to have to find a parking lot and all these things. It's just for a car, but if you want to do, for instance, aviation security, you're going to have bigger problems. Medical security, 5G and 6G networks. These are things that we would like to have access to. And so Cyber Campus Sweden is also intended to provide that within the cybersecurity area. So I think that I'll end there. And I am prepared for any potential questions.
Thank you very much.
All right, good afternoon, everyone. Welcome back. I hope you had a pleasant lunch full of networking and interesting research discussion. It is my pleasure to chair the afternoon session of this initiative seminar and to introduce the next plenary speaker, Professor Tamara Rezk. Tamara is currently a research director at INRIA in France, where she leads a group focusing on cybersecurity. And since this year, we have had the pleasure to have her as part-time guest professor here at Chalmers, thanks to a prestigious grant from the Wallenberg program on autonomous system, AI, and software. Tamara's research is focused on system security, and some of her current research activities include JavaScript security and microarchitectural attacks and defenses, which will be the topic of today's talk. Please, Tamara.
Thanks, Giuseppe, for the introduction. Thanks, everybody, for being here, and thanks to the organizers for inviting me here. It's an honor for me. So the topic of today is about Spectre Attacks and Beyond. So if you're working or if you're interested in cybersecurity, you have probably heard about these attacks already. Or even if you're not interested in cybersecurity, but you read the newspapers, you also know about them because they have been all around the world, in all newspapers in 2018. At the beginning, in January, around the 3rd of January, these attacks made the way to the news because they were new bugs that affected CPUs. And these bugs, the first of which was Spectre and Meltdown, actually, two of them, affected almost every computer system that will utilize any modern processor. So much they affected these systems that they opened what we call a new era in security, which is Spectre era. Since 2018, there has been many more of these attacks, not only Spectre and Meltdown. You can observe, you see the logos are official now. The new fashion is that attacks come with a logo. And, well, some of them, they don't have a logo, so they don't appear in my slides, so too bad for them. So they have become my favorite topic of research. And what I do for working on these attacks is build formal models of a processor in order to understand these attacks better and build robust verification systems, detection of these kind of vulnerabilities, and even recently open source new hardware in order to deal with these attacks. The way in which my team and me and I build these models is by using mathematics, formulas that will model the processor. We then test these formulas with current known attacks. And if the semantics, the formulas are not good enough, then we repeat the cycle. So what is interesting about this kind of research, and what is also fun, is that these models not only allow us to reason about attacks that currently affect CPUs, but also they help us to predict new attacks that will happen, for example, in future processors. For example, in the first model we built of a processor, we discovered that some optimizations to processors, if they were implemented, then they will lead to new class of Spectre attacks. And guess what? Like a month later, AMD released one new processor called Zen 3, and this was implementing the optimization we had predicted already. So it's a lot of fun, but this is not what I'm going to be talking today. In this talk, I will focus on the following question. If you are interested in cybersecurity, and particularly this workshop on a seminar on the landscape of cybersecurity, then why should you care about Spectre and beyond? So that's the question we want to answer here. The short answer, but I will develop this over the talk, is because they break software isolation and they depend on hardware, so they are not easy to fix. So in order to start with this topic, I will give you a little challenge. I know it's after lunch, it's difficult, you are all tired, I know. But let's try to think about this little problem. So hello world, you know, first program ever. Don't read, please, the C code there. It's just vanilla C code. It's standard code to implement a little program that is going to be receiving an input. It will receive an input, and then with this input, it will just remove the first word of the input, and that's it. The result will be what is left of the input, okay? So this is my question to you. If we have a C program, and this is really whatever you will write if I give you this assignment, like there is no trick, there is no special code here. It's just implementing this task that I told you. So if we give an input, which is hello world, what should the result be of that program? So during my talk, I will explain what can happen here. But in the meanwhile, I will let you to speculate between two options. So the answer to this question might be option A, word, the word word, or option B, the cryptographic key of another user in the cloud. For now, I let you think, and let's start really to explain these attacks by a 2-minute crash course on CPU performance. So these are 3 lines of code. Don't worry about what these lines are. It doesn't matter. It can be any assembly code that you want. But when a programmer looks at 3 lines of code, the programmer will think that these lines are executed in the order of the control flow in which the program is written, right? Like the first instruction first, the second instruction second, and so on. However, when you're executing this in the processor for real, there will be different units, and the instructions are executed by going from one unit to another unit. So on my slides, you can see 3 units, but there are more in normal processors. Just for the illustration, let me show you that each unit can hold only one instruction at a time. For example, the first stage here will be to fetch the instruction and then to decode it. But then in the second instruction, the processor will notice that the first unit is already free. So it will go and fetch in parallel the second instruction. So now we are executing the second instruction, but because this is a branch instruction, the processor will not just wait, okay, for the result of this instruction to be continued. You can observe here in my second instruction that there is a branch that is conditional on the condition RV less than 4. But RV is part of an instruction that is being processed in the first instruction. RV is being calculated, but because we are doing this in parallel, we don't know yet the result of RV. So instead of just stalling the pipeline, stalling every process of processing of instructions, what will happen here is that the processor will speculate, will predict what will be the result of RV less than 4 in order to continue with the execution of the instructions. So for example, here the processor will predict that the branch is true, in which case the instruction says, if the condition is true, go to instruction 3, otherwise go to 5. So we go to 3, but the processor will do that in a kind of execution that we call speculative execution. So what does it mean? This means that it's based on a prediction that might be false. And then we can continue. The processor is still maximizing the occupation of all the units in hardware, and this is perfect for performance. You can see everything is maximized here. And what happens if this prediction that I tell you, that which is, of course, based on algorithms, and these algorithms are usually secret, kept secret for each hardware manufacturer. These algorithms are very private because this is what makes the performance better. Then what happens here is that if the prediction is false, like it was not correct, that's not a problem, and everything which was speculatively executed is removed from the parts that are visible to the programmer. For example, the memory, there will be no traces there about this speculation. So everything is rolled back, speculative execution is reverted, and when a speculative execution is reverted, we call this transient execution because the execution disappears from everywhere, and then all wrong computation is thrown away. And this works really nice for the programmers because all these hardware optimizations that are there, they are transparent. They don't even have to reason about that. They just reason about the instructions executed in order, which is not true, as you can see in real hardware. But there is a detail, which is the observation that was made by these first attacks. Cache state a memory that is in the processors in order to accelerate the access to memory is not reset with wrong speculation, with this transient or speculative execution. And because of that, the Spectre attacks came to life, let's say. We could see them already. And this is the very first Spectre V1 attack that I was telling you about that made the news to every newspaper in the world. So it's only 3 lines of code, but 3 lines of code is efficient in this case in order to obtain information, secret information from other processes. So let me show you how it works now that I have given you this crash course of 1 minute on CPU performance. So again, we have here 3 instructions, the V1 Spectre instructions, and we have some registers and some memory which contains public information, but also a secret. In this case, a secret key. We also, I'm also showing on the slides some other part of the memory, which is what I told you, the cache memory, which is fast access memory for the hardware. And we will execute as before, like fetching, decoding, and so on, the instructions. And at some point, we will go to some speculative execution again, because there is some branch that we don't know, so the processor will continue with the pipeline by just speculating on which branch should be executed. At this point, there is a load. A load is just bringing something from memory, like reading memory. And this access to memory will make that the information that is in that part of a memory goes to the fast access memory, because the fast access memory, like the cache, is going to contain whatever is accessed recently. In this case, because we are accessing the address 40 plus RA is 9, we'll have to put this key of the secret B, the bit B, into the cache. And so far, there is no problem. But what happens now is that when we do a second load on the address 44 plus RB, and you can see on the registers there that RB now contains one bit B, which belongs to the secret key. Now, this address is also going to cache, because, as I told you, the hardware will, every time you access memory, will bring something to cache. And once there is a secret on the addresses of the cache memory, an attacker can just go, because a cache is some memory that is shared among all the processes, can go and just probe each address of the cache and recover the secret by understanding which parts of the cache memory is accessed faster than others. So in this way, an attacker will recover all the secret key bit per bit. So this is the first Spectre v1 vulnerability. But we are, I was explaining here just an attack that appeared in 2018. And we are in 23 now. So something has to happen in the middle, right? Like, is the state of CPU bugs getting better today? No. Like, exactly 2 months ago, I was in Usenet Security, which was surrounded by 2 major hacking conferences, DEF CON, Black Hat Security, and I was hearing to the presentation of these attacks, Downfall and Sandblade, which are, guess what, new kind of speculative attacks, or these CPU bugs like Spectre. So, what happens with these attacks? Don't worry, you don't have to read the code again. I'm just showing you which are the vulnerable snippets of code that will be vulnerable to this kind of attacks. And I'm also showing you that Sandblade affects all, not all, but Zen2 AMD processors, and Intel is, and Downfall is affecting Intel processors. And you know, if you have seen some assembly code in the past, you will know that the instructions that are on the slides are not common x86 instructions. Actually, these instructions that are here used for the victim code of the attacks, they are extensions of the x86 architecture. And they are using some registers. You don't need to read the code again, but they are using some registers that belong to these AVX instructions. And these instructions are used for fast mathematical operations, okay? So, okay, we have some victim code, but maybe you think that these kind of instructions that are just used for math operations are not very important if we have that code will leak something on math operations, right? But the thing is, there are 2 things here. In these 2 attacks, we have that these registers that are used for AVX instructions are shared in the same CPU, in the same core. Every code that is executed in the same core will be sharing the same registers. And now, if I show you again the Hello World program that I gave you at the very beginning, and we try to zoom in on the function string length, which is a common, C function that is used for strings, but there are many other functions that are used for strings, and we go to the implementation of that function. You will find the implementation of that function in the libc library of the Linux kernel, for example. you will see that the instructions that are used for the implementation of those, functions for strings are also AVX instructions, which are the ones that were used for downfall and assembly. And yeah, now think about this. The AVX instructions can leak a lot of things that are put in the registers when you use them via downfall and assembly. And now, these string operations are used everywhere, in every process. In particular, when you're computing user input, passwords, cryptographic keys, everything goes through these instructions and these registers that can leak. So I think that is bad news for security. And my question to you now is, did you speculate well what was the result for that little program I showed you at the beginning? Okay, because we are in a seminar on the landscape of cybersecurity, I just wanted to show you, I told you about Spectre v1, which is just one attack, and Assembly and Downfall, which are kind of the last attacks on this area, but I wanted to show you some slide with the complete landscape of all the families of attacks that are Spectre and beyond, like all the kind of attacks that we have had. Like at the beginning, I told you there is Spectre and Meltdown, but they were quickly followed by many, many, many other attacks that are following this idea of using leakage via speculative execution. And there you have I hope, all the families. And each of these families contain many attacks, and each of the attacks are leaking through different microarchitectural components, not only the cache. In particular, Assembly doesn't even need a side channel attacks, just the registers of AVX instructions. And if we zoom in just one of these families, because we have only limited time, we can see that since the attacks appear, always there are some mitigations and defenses that are proposed. For example, for the kind of Spectre family, we have defenses that work both in software, in hardware, in browsers, like site isolation. They are implemented in browsers. And you know what? After a defense appears, sometime later, we have that they are broken. Like all the defenses that are read, just for this family I'm talking, like this family is Spectre. I show you a whole list of families there. There, you can see that 2 of the defenses of this family were not broken yet. So that's not so good. So these attacks are not a solved problem yet. So why in the title of my talk I told you that these attacks stand apart? Why these attacks are not just another buffer overflow? The reason they are different is because these attacks have changed the way in which we reason about security. Before, we thought about security and we'll be happy with reasoning at the level of the software. If we will solve our software were completely secure and we will rely on the abstraction of the architecture that the hardware was giving us, that was enough, that was good enough. Today, we know that that's not enough. And these attacks obliges us to also reason about hardware and implementation details of the hardware, like performance, like branch prediction, like speculations, if we really want to achieve security when we execute the code. And that's why these attacks stand apart. It's because they change the way in which we think about security. We really have to go all the way down if we want to have security today. So the other reason why these attacks stand apart is because they are difficult to fix. I have shown you this with some examples of defenses that were already broken. But one of the reasons they are difficult to fix is not just because we don't know how to fix things. We know how to fix things. We know how to reason. But CPUs rely a lot on private algorithms, algorithms that are there to sell more processors, to sell more CPUs. And there is a reason behind that. Each manufacturer, hardware manufacturer, wants to be, the best. But this is a problem for research and for, of course, people who build defenses, because we don't know what are the internals of some of the algorithms that are used, for example, to speculate. And then research takes longer. Of course, there is a lot of, in order to achieve all the results I have shown you in the slides, both for the new attacks and for the new defenses, there is a lot of reverse engineer that needs to be done before reaching the defense. We can still do it. It just takes longer. So, fine. I have shown you that CPUs have bugs. So what? Let me tell you about the implications. Some of the implications. This is not at all a complete list. So, for example, SGX, which is something implemented in Intel processors, hardware defense in order to isolate and execute code securely, is completely broken due, for example, some of these attacks, in particular, downfall, the one I just showed you, affects SGX. You can steal the keys inside the SGX, plain, just like that, very easily. LVI, another of the attacks that I showed you before, also broke SGX. And of course, there are hardware updates and there are microcode updates that you can do, but these microcode updates, they are not even available for all of the different processors that are affected. It goes without saying that you can also, even with the attack I show you, the assembly attack, you can also steal cryptographic keys and other sensitive information. I think it was, I don't remember if it was downfall or assembly. One of those was just stealing everything that the user will type, like in seconds, like on live. Another problem is, another thing that these attacks imply is the breakage of isolation in memory. So usually when you have the kernel, you have some, kernel mode, user mode, and these two things are separate words, and then you can just, by user mode, use some syscalls from the kernel and things like that. But by using these attacks, again, these isolation barriers in the operating systems, they are, again, broken. And even better, there are some of these attacks, in particular blindside, one of the full list of attacks I gave you, they also have the potential to make some old attacks that we thought before 2018 that were like solved problems. For example, I'm talking here about code reuse attacks. I mean, if you're working on security, we know that, for example, control flow integrity should solve this kind of code reuse attacks. However, blindsides show us that by using speculations, these attacks become new again. These defenses do not work anymore. And what's even better, if you want, is that we don't know how to defend now against code reuse attacks. We don't know how to defend against blindside, for example. That's open question, if you want to do some research. So I hope I have convinced you so far that these attacks are important in the cybersecurity landscape. The implications are that ultimately these attacks violate all kinds of process isolations that we have implemented, kernel, hardware, everything. They stand apart because they made us think about hardware in our threat models. We have to consider hardware now. They are CPU bugs and they are hard to mitigate because many things of the hardware implementation are kept secret. But we all know the devil is in the details. Here is also the case. So what can you do about it if you are just a user? Well, the best you can do is keep both your software and hardware updated. Now, if you're a cryptographic developer, that's much harder, because now the things we were doing before 2018, you know, these constant time things for cryptography, they are not valid anymore. We have to take into account speculations as well. So if you are a hardware developer, a hardware designer, you know, architect, good luck. And some reflections that are, you know, my own, if you want, is that is it really a good idea to have this hardware as a black box? Or maybe these attacks are just opening a door, or opening an opportunity to work on new projects like open source hardware. And when I'm saying open source hardware, necessary, we are talking about RISC-V-based hardware. RISC-V is an architecture that can be used you know, for research, that you can actually implement RISC-V hardware. Whether if you wanted to use x86, like the Intel architecture, or ARM architecture, the ARM architectures, then you will need to pay royalties to these companies, whether RISC-V is open. And maybe we can, you know, find a new way to design processors which will not have all these kind of problems, but still keep the performance. So there are many research opportunities in this area, in particular robust defenses, how to defend against these old attacks that suddenly they are new again, and so on. So that's all what I had to tell you. So thanks for your attention, and I'm ready for questions now.
All right, so next talk in this session, it's my pleasure to introduce the next speaker, my colleague at the Department of Electrical Engineering here at Chalmers, Professor Marija Furdek. Marija's expertise lies in optical network design and optimization, with an emphasis on physical layer security and resilience. And in her research, she strives to develop secure, cognitive, and autonomous communication networks. And this is going to be part of today's talk. Please.
Thank you very much, Giuseppe, for the very kind introduction. And hello, everyone. It's really a pleasure to be here and to talk a bit about my research. I've been on maternity leave for the past 2 months, so my brain is not at its best, but I'll try to do the honor to the research work that we have been doing for the past several years. So I wanted to be a bit thought-provoking with the title, and then I decided to paraphrase a line from an old Hollywood movie called A Few Good Men, where Jack Nicholson passionately says, "You can't handle the truth." But I'm not that good of an actor as him, for sure. So I just put a question mark there and tried to dig a little bit into the shape of things when we talk about the security of optical network infrastructure. So this is basically what I'm going to do in my talk. I'm just going to first introduce a little bit the security vulnerabilities of optical networks to you. And then I'm going to talk about some security management challenges and what can be done to address them. And before I begin, I would like to express my sincere gratitude to my colleagues who have been contributing to this topic over the years, as well as to the funding agencies that have supported our research. So since I'm talking about physical infrastructure, the first question that I'm sure comes to your mind is, how physical is the internet really? Well, contrary maybe to a popular conception, the fact is that more than 98% of the entire voice, data, and internet traffic is actually carried by fiber, by optical fiber. And in that sense, we can consider the optical network as the spine of the information society. Optical fiber is deployed everywhere on different scales. For example, here we can see an image from the inside of a data center where the yellow lines are the optical fibers that connect the servers. Here is an example of a city fiber map for the city of Amsterdam, where the red lines are the fibers. Here is an example of a US fiber map, where you can see also the black lines represent the fibers. And finally, there is the network of the undersea cables that are actually interconnecting different countries and different continents. So since you can see here, the fiber is deployed beyond the secured perimeter, and essentially anyone with harmful intent can tamper with the fiber as they please, basically. So what types of threats jeopardize the optical infrastructure? There are two broad categories of physical layer attacks that are typically distinguished based on the objective of an attacker. So we have eavesdropping attacks, where the attacker is trying to gain access to the carried information by tapping the fiber. One method is shown here, where I don't know if you can see the laser here, but basically the fiber gets bent and the light leaks out of the bent fiber. And the other type of attacks are aimed at disrupting or degrading or completely disrupting the services. And this is done by, for example, disabling a photonic component, cutting the fiber, inserting harmful signal into the network, etc. So there are more overt and more covert methods of attacks. And probably, if I can read some of your minds, you are maybe forming the same question that I have been getting over and over again. Do people really attack the optical network? Like, who would do that? Unfortunately, it's not such a common question anymore, because we have been basically bombarded by a lot of reports of attacks on optical network infrastructure. And here I'm just showing a few of the headlines. For example, here you can see a fiber cut attack where the cabling infrastructure has been disabled, and it has caused disruptions in wider French metropolitan areas. Here's another example from the Bay Area in US, where this has been taken place over a series of attacks within a year and a half, let's say, and has been investigated by the FBI. Then here below, there's a report on teaming up of the Italian Navy and the telecom provider to protect their fiber infrastructure. But unfortunately, these news hit close to home as well. So here's a recent report. It's been a year ago. It happened in Germany, where there were well-informed saboteurs who knew apparently what they were doing. And by cutting just 2 fibers, they managed to bring down the entire regional train network in the northern Germany. And recently we are also seeing reports on sightings of suspicious vessels that are plotting, probably they are suspected to plot sabotage in the North Sea, where they are, it's assumed that they are trying to figure out how to tamper with the communication and, for example, energy infrastructure. So what can be done about this? Typically, when we talk about network security management, we distinguish 3 main pillars that are related to risk management, attack cognition, and incident response. You can also view it within relative to the timeline of an attack. So risk management is anything that happens before. Attack cognition is related to the event of an attack, and then incident response is related to recovery. So I'm going to walk you through these aspects, and I'm going to present different techniques that can be used to address these pillars. And I'm going to use traffic light assessment, right? It's simple. Red, good. Green, red, bad. I told you. Green, good. So let's start with risk management approaches. So when it comes to risk management, the first thing one would like to do is to identify security vulnerabilities of photonic devices. There is quite a good body of knowledge related to vulnerabilities of devices, but since new generations of devices are coming and new types of attacks are coming also, we can never really fully relax and say, okay, now we are fully green and we're done with this. Then the second part would be to characterize system behavior under attacks. Here we also have some quite good knowledge, but there are some methods, for example, some fiber tapping methods that are not fully verified. We don't know them well enough, and we don't know their impact on the system well enough yet. And in addition to that, the impact of attacks greatly depends on the system specifics. So, for example, for the same attack technique, if higher order modulation format is used for communication, then it might be more sensitive to that particular attack than maybe simpler modulation formats. And finally, using a kind of a bottom-up approach, we also need to identify the network-wide impacts of attacks on services that are running on top of the network. So remember, we are talking about physical infrastructure, but this same, one and the same physical infrastructure is used for communication for a multitude of services with very versatile behaviors, requirements, different protocols, etc. So we currently, to the best of my knowledge, there are no models that can capture these multi-layer interdependencies. So we cannot formulate the impact of the security breach at the physical layer to the network services running on top. And having all this knowledge in mind, we should then develop techniques to minimize the attack surface, so ways in which we can make the network less vulnerable to attacks. Then we come on to the attack cognition techniques, and here the key is to collect network monitoring data in real time. Currently, we have quite good device capabilities of the newest generation of devices. They are very good with telemetry. They provide a very rich data set related to the optical performance. But the challenge here is that it's not possible to monitor every point in the network and provide a very broad set of parameters for all the signals. And then whatever data we can get, the key thing to really achieve attack cognition is to analyze the data and achieve attack detection and or identification, analyze the root causes of different anomalies, and here we actually rely on machine learning techniques very extensively. One thing that should be considered here is that different techniques offer different trade-offs between precision and flexibility. What I mean by this is that ideally we would like to have a tool that gives us very fine granular information about a particular anomaly, particular attack, the type of an attack, the intensity of an attack, the location, etc. So one way about this is to use experimentally obtained data to train supervised learning models. But these models, they can provide high precision, but they are not flexible enough to address, for example, newly emerging attack types, attack techniques. And then on the other end of the scale, we have unsupervised and semi-supervised learning techniques that do the opposite. So they can be used to identify a previously unseen type of an attack, but usually they can only give us a yes-no binary information on whether there is or there isn't an attack. They cannot give us more details on the attacks. And finally, the third pillar is incident response. So here, the first step would be to localize the breach, identify the device or a link that has been tampered. And the challenge here is, again, due to the fact that we don't have monitoring information ubiquitously and very rich for all the network locations. Then the next step is to neutralize the attack and recover the services. And here we can react on a very small or very large time scale. For example, a quick action would be to bypass the breached link, reallocate resources to the affected services. And the goal here would be to minimize downtime or maximize capacity. Finally, we should immunize the network against future attack occurrences. So the idea is that when a same attack type happens again, the network already has a set of methods in place that can defend from that type of attack. So I would like to share with you just briefly just two recent efforts that we have done here at Chalmers related to attack diagnostics and localization of the attack source. So I will first begin with this physical layer security diagnosis workflow. This is an effort on an effort to try to come up with a, let's say, monitoring loop that can provide information about the detected types of threats. So basically, it's a monitoring cycle. So it begins by receiving an optical monitoring, an optical performance monitoring sample, and that's a set of analogous parameters about the optical signal. So, for example, the received power, chromatic dispersion, BER, etc. And then we run the anomaly detection, and we check if, in case an anomaly hasn't been detected, we just simply wait for the next sample. But what do we do here? How can we address both known and unknown attack techniques? One way to it would be to first run the supervised learning model. Here's the, I don't see the pointer. Ah, okay, here it is. So the first step would be to, let's try to check if it's something that the network has already encountered and we have already trained our supervised learning model with. If it's something that can be identified with this, with a certain confidence, then we simply return this class and we consider that the attack type has been known. So what's going to happen here in the main loop is that this knowledge can be used to pre-design some recovery techniques. If we are not satisfied with what was received from the supervised learning model, then we can assume that it's some threat that hasn't been seen in the system before. So we run the semi-supervised or unsupervised model that only gives us yes or no information about the presence of an attack. So in the main cycle, this will trigger further analysis for the root cause. I'm not going to go into details of this root cause, but the output would be a visualization tool, a visualization graph that will support the human security officer with further handling of this incident. So this is how we can diagnose individual connections. Then based on this information, we can further deduce the location of the breach in the network based on the security statuses of individual connections. So how do we do that? So basically, if we know the routes, this is a simple example where we have a network with 6 nodes. This is and they are connected with optical fiber. So we are only talking about the optical layer now. And we have 2 connections, C1 and C2, that are they are established on top of this infrastructure. So for each of these links, based on the attack type and the behavior of a specific attack, we can identify the subset of connections that will be affected. And this means that the bit will be set to 1. Otherwise, it's set to 0. So for example, if link AB is breached, then connection C1 will be affected. And this actually gives us so-called attack syndromes. These binary words, we refer to them as attack syndromes. And if they are unique, then based on the subset of affected connections, we can already deduce where the breach happened. And in case they aren't unique, which is the case for these subsets of binary words, we need to add some distinguishing bits to them. So we add connections to the network that will serve to distinguish between the different attack sources. So we achieve this disambiguation by adding connections C3, C4, and C5. And this is actually a very complex but nice optimization problem. So there is a framework for optimizing the set of connections that need to be added to the network to fully achieve attack source disambiguation. So this actually brings me to the conclusion. I hope that I managed to convey to you that we do need better security management techniques for the optical network infrastructure, because typically the upper layer people who deal with upper layer services, they consider the infrastructure as like perfect fat pipes that never have any issues. And this doesn't work with a vulnerable physical infrastructure. One of the needs that is required to improve security is behavior characterization for photonic networks and services under attacks. And one of the aspects here that personally I consider it key is the multi-layer security interdependency modeling and consideration. I think if the Deutsche Bahn network was aware of the vulnerabilities of the physical infrastructure, they would have planned their network differently, and no two fiber cuts would bring the entire network down. And finally, we need also new approaches for physical layer attack diagnostics and remediation. So I would like to thank you very much for your attention, and I would be glad to take questions.
So, very welcome to this final session. My name is Thomas Olofsson from Chalmers, and I will be leading this Q&A session at the very end. And here we have gathered the 4 of the external speakers. You recognize them from the talks earlier today. And we also have 4 industrial representatives, mainly from the, well, with a focus a little bit more towards the automotive domain. And since you have not met them, maybe you could give a short presentation. So, Bruce, would you like to start?
Do you hear me? Good. My name is Beruz Sangchuli. I come from RISE. For those of you who does not know RISE, it's the Swedish Research Institute with about 3,000 employees spread all over the country. I'm almost an infiltrator right now because RISE is in between academia and industry, so I'm sitting with all these other industrial representatives here. And I work mostly with safety and security. I've been spending a lot of time testing systems with respect to the safety properties, and I've been also looking into the impact of security attacks on system safety.
Jonas Magasinius. I'm from Assured AB, and we do technical IT security, advisory, penetration testing, secure development, and also some research. I have a background in security since 20 years, roughly, and also here at Chalmers as a PhD student previously. CEO of the company, but still sort of involved in testing every now and then.
Hi everybody, Nasser Nodehi from Volvo Group Truck Purchasing. My background is in information security, and at least for the last 10 years it's been automotive cybersecurity. Just like Jonas, I've been also studying at Chalmers, got my PhD under supervision of Thomas in automotive cybersecurity, and so I've been working with different types of vehicular communication technologies from V2X to IDS and stuff. Thank you.
Hello, my name is Kim Strandberg. I work at Volvo Cars. I'm an industrial PhD student at Volvo Cars and Chalmers. And my research is mainly about resilient design and also secure software update and forensics.
I don't think you need to introduce yourselves. Yeah. If you want.
Should we introduce ourselves?
No, I think we know you, so thank you. So the session, what we will do here is that I have, of course, lots of questions from the previous talks, from your talks, which I will try to bring up and ask the panelists here. And, well, last time I did this, it was a failure from my side because I had 10, 15 very good questions. I was very proud of the questions, but the debate started and I never got through half of the questions even. So I have to scrap them. They remain on paper. We'll see what happens today, if I can ask my questions, or if we will have a debate that is kind of self-contained and continues between the participants here. In the end, we will also open up for questions from the audience. If you have questions later on, you will have the possibility to ask questions as well. So what we have here, the industry representatives, it's a little bit of a focus towards the automotive industry. And the reason for that is because well, of course, we have Volvo Cars and Volvo Group in Gothenburg, but it's also a very complicated system to secure. You can say it's an IoT device, it's connected to the internet, it's connected to other vehicles, you connect mobile phones, wireless LAN, lots of different things are connected to a vehicle today. The complexity is quite high. You have, in a not very advanced vehicle, you have more than 100, maybe 150 computers on the inside. It's not even close to autonomous, no autonomous functions at all. Still 100, 150 ECUs or computers on the inside, connected on various internal networks. And it also communicates with the outside. You have something between 100 and 150 million lines of code on the inside, which we need to secure. And as we heard before from the talks here, this is complicated, and even a Linux system with 50 million lines of code, which could be part of these 150, still it's an extremely complicated system. So what we will discuss today is a little bit IoT devices, complicated IoT devices, how can we secure them? And one thing in the first talk by David here, you mentioned that maybe there's time for another alternative routing scheme for the internet. And if we look at the automotive domain, would it be possible or useful to have such a domain for the automotive, for cars or vehicles, say, that they can only communicate with themselves within that domain, maybe get software updates over the air from the vendors? Or is it, how applicable would your approach be to the vehicle domain? No?
I just speak, okay. So I think it would make a lot of sense, and you had all of the perfect use cases for it. Vehicles that need to be upgraded, vehicles that speak with each other, vehicles that communicate with roadside infrastructure. You would like that, somebody on the side of the road with some software-defined radio isn't speaking to your vehicle, but you would like maybe other vehicles to speak with it. By having effectively an isolation domain, that would be like creating this closed communication environment where you basically limit who can speak with your cars. This makes a lot of sense. A similar motivation can be used for IoT. For IoT devices. I mean, whether it's a car or an actuator, from the abstract network perspective, doesn't make too much difference.
But what would happen if you have 10 million cars, for example, in Sweden? Wouldn't that effectively be more or less an internet?
Okay, good. The question is where you would draw the limit to this isolation domain. If you would like to consider cars in Sweden, cars in Europe, cars worldwide, maybe not cars worldwide, because then a car in some country that you might not trust might be able to communicate using this isolation domain with a car in your country. So we'll have to think a bit about that. That's not so much a concrete technological problem with sign, it's more a question of how you set up trust relationships and then map them onto this networking architecture. So that would require some thinking. But it's not unsolvable.
I heard someone from BMW saying that they might consider their own internet for BMW cars. Is that something, would that make sense?
I'm having trouble with acoustics, so I missed a few words with BMW cars. What would?
BMW said that they might want to have network for their own, between their own cars only, to not let anyone else in on that network. So
yes.
would that make sense?
Yeah,
or
SIAN could be a good starting point for that. Yeah, it could indeed make sense.
Okay.
Because one can have hierarchical isolation domains. One could have a car isolation domain. One could have a BMW isolation domain. And then, depending on the different use cases, you would do communication within one or the other. This is possible.
Mm. Okay, I don't know if you have any comments from, Jonas?
I'm a little bit curious, as my perspective often is from the point of an attacker. I would use my vehicle as a gateway into this separate network. How can you restrict that? Or how can you make sure that it's not possible?
It may indeed be possible. So, for example, for interbank clearing, if Zurich Cantonalbank wants to attack the Swiss National Bank over SIAN, they could do it. But it's a much, much simpler situation to figure out what's going on within the Swiss financial isolation domain, that if somebody randomly somewhere in the world over some compromised computer starts attacking you, you can take legal action against them. And there's various countermeasures that you could take if you know which Swiss bank is attacking you versus somebody somewhere in the world. And one would have to think about that in the case of autos. So if it were indeed BMWs, okay, good. If somebody could attack a BMW car using its bus system and use that to attack another BMW car, that's not good. It could happen. Of course it could happen. But at least BMW would somehow be in a situation where they could analyze the problem, think about fixes, implement them, roll them out, etc.
And maybe I can also ask a question. So if, in terms of trustworthiness of the communication and authentication and authorization type of services, do you think already established solutions like the PKI solution that we have in the HCITS would be sort of reusable to some degree?
Indeed. So, for example, in SIAN, the payload is not encrypted. So typically, if you're worried about confidentiality and integrity of the payload, and you are, then you use your own security solution. For example, you run your communication over VPN. So first it hits your VPN, and then it's turned into the IP packets are turned into SIAN packets.
Okay.
Yeah.
Thank you.
I can mention that actually the same concepts we use within vehicles as well, as Thomas mentioned, that there can be over 150 vehicle computers, and we also try to do this domain separation as well in vehicle to separate the safety critical systems from other ECUs as well. So we try to have this different concept of domain separation as well, yes, as in SIAN. That's a side note.
Okay, thank you. We have had several talks about cryptography today, and Marc, you mentioned the impact of crypto agility. And, well, one takeaway is, of course, that cryptography is complicated, needs experts, and can we trust the automotive companies to actually implement this in the correct way?
So the question was how to ensure that's correct implemented.
Yeah, well, implement. I mean, you have to select the right ciphers, the modes to use. You integrate a lot of components together. Things need to match. We saw Elena's talk earlier, the contacts that didn't match.
So actually, I think especially the automotive domain has some additional challenge because of the depth in the supply chain. So usually you have tier 2 suppliers for the hardware, which are not the same as the software suppliers, which then are used by tier 1s, which are then used to, let's say, put things together, build a security architecture on component level, while the OEM usually put the overall security architecture. So you have intermediate layers there. So answering only the question how to ensure that the software is securely implemented, I think is not reaching far enough. For secure implementation of cryptographic algorithms, I would say we need to shift the way how we develop
schemes or how we implement it. One direction, actually Pontus was pointing out, we need tools to actually verify that the algorithm we are implementing is actually doing what the implementation is exactly doing what the algorithm meant to do. So one hint there was something like a machine provable schemes, so something like Jasmine, for example, which is a programming language where you program in a, let's say, assembly-like way, and as a byproduct you get a framework which you can prove by EasyCrypt, so that you can prove that the algorithm you're implementing is correct. But on the other hand, you still have the issue of using your cryptography wrong, which means, let's put it this way, from my experience in automotive, you have a hard constraint on resources, which sometimes leads to optimization ideas. And the biggest issue in security is optimizing. So all the implementation flaws, or most of the implementation flaws I've seen comes from, I have an optimization idea. And this is actually a challenge. So just for what I would say for the current automotive architecture you're saying with like 100 to 150 components. When I think about going further in the new architectures, which seems to be on the horizon, like the software-driven architectures, where you have like 4 main domain controllers, which are the powerhouse for computation, and you have then only the sensor and actors, which are a little bit smarter. It's been more challenging because then you have like a generic platform, so you move more from the embedded security domain, I would say, to secure code, to the domain where we are now with IT security. So you have more flexibility, which opens more possible flaws. There also, I think, we need tools to support, otherwise not possible. And on top of that, I think the really challenging part in automotive is if you have some kind of new automotive architecture where you have, let's say, processors which are more powerful, the domain like a modern smartphone, for example, you can do a lot, but then you have smart sensors which are not so powerful. And then you need to find a good combination of implementing crypto, which is running on small resources and can run on bigger computers with more power. So, and this is also a challenge. So I think it's just assuring that the software is written correct is just a tiny step in the architecture, because how I see this modular architectures in cars are very complex and need to be generic as well, because for sure one OEM has some architectural plan, maybe a platform plan. Some OEMs have platforms where they build different cars or different models based on generic platform. But when you look again into the supply chain, the tier 1s and tier 2s want to have generic procedures. And there comes the really big effort in trimming the security solution or philosophy of one OEM to a generic platform. And this is a challenge on top, next to just securely implemented in software. Maybe I can quickly add something along the lines of what you were saying, is that another challenge is that, for instance, at least in the automotive industry, there are customer rights, just like anything else, that where I, as a customer, I get to take my vehicle to an authorized workshop, and they're like, I should have similar the choice to take my vehicle to basically any workshop that I want. So the choices that I make as OEM from a cryptography perspective, that would also mean that if I update my methodology and I use something, a specific method, then that means that the entire chain needs to be up to date. So that third-party workshop that probably has an old diagnostic device, that also needs to be updated. So at least from a legal perspective, there are also challenges as well.
Yeah, you're right. So a legal perspective, and especially when you have the case, I mean, you can buy a car in Europe and drive from Europe to Asia across the border. So you're entering another legal perspective room. So the question is how it's handled there. So I think in Europe, everything is quite aligned regarding security, but when I remember, we had a lot of discussions back then when they came up with a new law in China where they want to harmonize the cryptographic algorithms for China. So you want to deliver worldwide. So it's a stretch actually to have exchange the algorithms but maintain security as well. Yeah.
Okay, we also discussed earlier open source, the problems or the maybe benefits. I think Tamara mentioned open source could be nice when you design processors. Pontus said the opposite, I think, when it came to using libraries and stuff, open source software that you just pour into your designs. How should we deal with maybe how should we treat open source? Is it good or bad, or what should we think about? I mean, this is a constant debate. I mean, I've seen this for the last 20 years, probably.
I personally don't believe in security by obscurity, so I think it's a good thing to have an open source code so everybody can have eyes on this. And when it comes to hardware, like no one is really using this for real open source hardware, but I think that could be one way to go.
I think it might make sense, but it also means that someone can actually, like you said before, there's some trade secrets in the design which might be very hard to foresee or for someone else, for an attacker to find. But if it's open source, you can immediately find it and, well...
I mean, yes, I mean, this can happen, but in that case we can have better detection methods in order to avoid this. I mean, maybe.
Well, I think open source is a great thing. I think it's pretty amazing that it's possible for us to cooperate so much in the development, and it's very obvious. For instance, the Linux system. It's obvious that how important the open source community has been for the development of our digital society. So I think the benefits of open source are difficult to underestimate. Overestimate? but of course there are problems. Like in my talk, the idea that all bugs are shallow for many eyes. There's some expression on open source that it should be easy to find the bugs if many people are looking. But that turns out that that's not always the case. Bugs have been hiding in open source for decades, in plain view for everyone. And it's also the case, as with the Pegasus software and NSO, that open source also makes it easier for attackers to find vulnerabilities that they can exploit. It's more time-consuming to find vulnerabilities in proprietary software if you don't have access to the source code. So I think can't be overestimated, but it's really there are pros and cons. There is a new law that's directed from the EU, the Cyber Resilience Act, which is going to, I think, influence a lot how we think about software development and security and software development. Very, very hefty fines on companies that develop insecure software. I think it's 2.5% of yearly revenues. That can be a lot of money. I know that they have a carve-out for open source. So the way I understand it is that as long as you don't make money on what you're building, because it's based on revenue, maybe that comes from there. But I've also understood that this is not an easy carve-out, that there are difficulties in how open source then becomes integrated. And if you have draconian regulation on software development, can also stifle innovation. So I think there's a difficult balance between the benefits and the drawbacks.
I'd like to argue with you on that because, it's true you can introduce more vulnerabilities. For example, if you have open source operating system like Linux, But there are also more eyes to look at this, and this really helps. For example, if in the case of these attacks I was presenting today, you can go to the Linux kernel and check which is the micro-op, the last hardware update that I had that Linux has in my computer. If maybe I am using some other operating system, maybe I couldn't check so easily these kind of things, or I think it's more difficult to, I mean, it's arguable, but it's more difficult to introduce vulnerabilities when everybody is looking at you. And when it is, you know, a bit hidden, take, for example, again, from the recent conferences in security that happened in California last August, take, for example, these protocols for radio communication that were broken just because they were the cryptographic algorithms there, they were hidden, the Tetra protocol I'm thinking about. It's not because they were, the source code was hidden that now they are not broken, it's just, it was hidden for decades, and in the Linux kernel, I think these kind of things will be much more difficult because of all the eyes looking at this.
Yeah, I also would like to comment on that, because you mentioned something in your talk earlier. We have a massive lack of experienced people in security, and I think this is a side effect. So if you do if you put something open source, but we do not have the manpower that a lot of people can look at it with a certain knowledge and background, you won't find it. And I think open source software and hardware would be interesting, especially in the perspective of common criteria certification. You mentioned the Resilience Act, if I'm not wrong. They also discuss now if IoT device should have a hardware security module included, which translates for some applications, they need a common criteria certificate. And if you go for common criteria certification, you need to show how hard it is to attack a scheme, and you get, let's say, you can increase the effort of an attacker if something is secret. So if it's open source, you can still get the certificate, but it's way much harder to prove that's secure. But on the other hand, it's more like an check how you trust how well that is designed. And in this enlightenment, I would be keen to know what the industry thinks about open source hardware, especially when you think about, especially in automotive, you have the second source issue always. You need to have a second source in case some of your suppliers are cut down or had an issue with delivery. And I think with open source hardware, you're shifting this second source issue from the manufacturer more to the fabrication point. And I would really keen to know what's your perspective on that.
Maybe I can start. I think it's actually, I can personally say I've never thought about it. This is an interesting idea. I think I need to think a little bit about the security aspect as well when you have the same, so when it comes, essentially what you're saying is that you have the same, it's an open source model and then you can basically manufacture it. And that means that everybody get to use it. So I think it has its own benefit, but at least from a security perspective, what I think on the surface I can see is that if there is an inherent vulnerability or problem with the hardware, just like the software version, that then everybody who uses that piece of software will be affected. So the same story applies here as well. And the problem, I think, at least with the automotive industry, as you know it, is that unlike the software world, well, chances that your update reaches the destination is way higher in the software world than like in the automotive industry, where chances that you can really do what they call it recall and change and update the hardware is chances are not really high, I would say.
I'm not from the automotive, but to me the problem is not whether open source is good or bad. let's say we have open source, we have RISC-V hardware that you talked about. If we don't have the tools to find the problems, and we just need to wait for someone to go find them, if we don't have the automation that allows us to do automated fuzzing of these systems to find the problems, what's the point of having open source or not? So what I would say we should think of more is basic dependability concepts, building reliable systems from unreliable components. We just need to accept that vulnerabilities are there, and if they get exploited, where do we detect them? Where do we handle them to mitigate their impact?
Why do you say we don't have tools for fuzzing hardware?
Sorry, I don't...
Why do you say that we don't have tools for fuzzing hardware?
I said we don't have tools that can in an automated way go through a hardware and figure out all the problems and brings it out, because we have limitations there. There are tools that can do this, but if we could automate them and let them do the work, then why do we need to wait every now and then for someone to figure out these vulnerabilities and continue to have vulnerabilities after patching? So to me, the tools need to be there. We need to get support from any domain that can allow us to build these tools, improve them so that they constantly look for these vulnerabilities. Then we can say, okay, open source is good because then we can have access. But then if we go with open source and then we expect the problem to be solved, it's not the case, because the tools need to be there to support us.
I think like one of the attacks I was talking today was discovered thanks to fuzzing hardware, like new technique like made by some researcher in Google. And I mean, of course, this was black box because these AMD processors, you don't know what's inside. Like, but still, if you had the code, maybe you could do something much more precise than the fuzzing that is done today. Because as I told you, in August, this attack was discovered by fuzzing the hardware in a black box manner. So I think open source will also help there. Like, these tools exist, they are there, they are used, and they have discovered very serious vulnerabilities, and they can be improved if you can see more.
So I don't think that it's necessarily so that that closed source it's more difficult to find attacks in closed source software. For example, if a vulnerability is patched, it's rather easy to look at the patch to pinpoint the exact part of the program to attack. So that's an end-day attack. It's not a zero-day. It's not finding a new vulnerability. And fuzzing is a really good way to find vulnerabilities without necessarily being able to pinpoint. Well, taking some time. It takes some time to actually pinpoint where in the program it's the vulnerability is. And now I'm going to contradict myself. So, on the other hand, when I do penetration testing, it's so much more easy to find sort of a hint of a problem and look at the source code. So I believe that open or white box testing is much more efficient and it's much more precise. So yeah, I'm contradicting myself, but it's not impossible to find vulnerabilities in closed source software.
So one detail, it's not only about finding the vulnerabilities, it's also about understanding if the fixes for these vulnerabilities are correct. Just to mention one example, in the talk of Pontus today, there was this, you show some vulnerability and then some fix in the kernel, and you know, this is exactly a Spectre v1 attack gadget. So it doesn't mean that the fix doesn't work. It just means that you can see that a fix may also lead to another vulnerability, which is not the one that was fixing. And people, I mean, I don't know how they are fixing vulnerabilities in Windows, for example. I cannot see the code, but I can see the kernel code. And then I can know, I can go and explore myself if I want. And many people can do this. And this helps, I think.
Okay, thank you. You also mentioned a little bit about legislation and standardization and, for example, upcoming legislations from the European Union regarding digital devices. But you have, in the multi-domain, you also have standardization, rather new standardization for type approval and so on. To what extent does that help you with security, or is it like always, standardization is one step behind and it's a committee work that everyone can agree upon, but you need something else? Does it help with standardization or, say, the type approval, for example?
Because there's a little bit of echo. So your question was that whether the existing of standards and type approval and all of these legislations.
Yeah, will it help you, or is it something you standardize something which everyone already has, or does it really drive something forward?
Oh, definitely, I would say. I think if you have been working in automotive industry, probably a few years before the ISO SA 21434 was released, and a few years after, and also probably before the first, before July 2022, where the UNR 155 and 156 came into effect. If you just compare the last couple of years before and after these dates, I think it becomes quite clear that the standards, and I would say more than the standards, regulations are quite effective. So I think no doubt about that, but at the same time, I think what I personally think needs a little bit of more attention is how the regulation is being applied. Because when you do certifications and when you do type approvals, I think it really comes down to who is conducting the audit, who is conducting the type approval. And that really, I think, is an area where more attention needs to be paid, because if, just like, let's say, an ISMS certification for ISO 27001, if the auditor is not a good auditor, then you might get certified, but that doesn't necessarily tell anything about the quality of the product or the quality of the management system necessarily. So I believe the same type of, we need some improvement in that area.
Yeah, I can just mention also that the regulation is also a very high level, so we don't, you also need to have all the manufacturer also need to provide all the details. So it's also important to understand that the future will become more and more details. So it's up to the automotive manufacturer to provide all these details, which is actually not included in the regulations today.
I think there are two sides of a coin, because for standardizations it should not be technically too much focus, it should be freedom for implementation. I think this freedom of implementation, which gives you a framework with the ISO 21434, is actually the downside when you get audited, because it leaves freedom for interpretation. And I agree that I guess there needs to be some work done, and I think the next step should be to, like an ISO 20000 family, you have a specific chapter or family actually for auditing, and this is missing at the moment for automotive. But I think when this comes, as I see the 21434, it's a good step in the right direction, but it's a very broad and, let's say, flexible framework. It more or less says to you, you need to do something without any measure of quality. Yeah? And when this next standardization would come in order to that, what you need to do for an audit, I think this will have an effect on the ISO 21434. I think it's a step where the automotive industry needs to grow, and I know it's difficult because since automotive is an international business, and therefore you have a lot of parties and a lot of legislations you need to align. So I think in general it's a good first step to ISO 21434, but I'm really looking forward that it becomes a family of standards like the ISO 20000 family.
Okay, should we open up for some questions from the floor? Do we have questions here? Yeah, I see one hand up there.
So hopefully you can hear me better now from the back instead of from the front. I was very interested on the discussion you were having about open source and the security implications it could have. But I noticed that you were mostly focusing on...
Can you speak a little bit slower, please? It's hard to hear.
Sorry. I was seeing the discussion you were having on open source and the implications it could have on security. And I noticed that you were mostly talking about what happens when somebody attacks and when somebody defends. I wanted to ask instead about what happens afterwards. How could open source influence the forensic efforts that are made after an attack happens?
Can you repeat? I didn't hear. Was it about forensics, what is required?
What happens after the attack, I guess, with respect to forensics?
It's a question that how you have the traceability for what has happened.
How open source can improve, help, for instance, in forensic.
Yeah.
So the question is how open source can help in like there are, of course, offense and defense side. So if we talk about, let's say something has happened now, we're going to do forensics. Could open source
Maybe you should have a microphone, Nasser.
Okay, yeah. I think definitely. I'm not a digital forensic expert, but from what I know, if just I step away from automotive, there are a lot of open source software out there, especially when you look at two specific areas of forensics and also threat intelligence. A lot of good tools out there. So I think that's probably one area where open source is definitely helping the security community quite a lot. But of course, I think just like any other software, one needs to be careful about really verifying how secure these tools themselves are. Because, I mean, I think that we had this talk earlier in the morning about Linux kernel, and you know, people try to fix vulnerabilities in a piece of open source code, and then you could, if you want to, if you're lucky also, you could basically inject a new vulnerability and then misuse it. So if the same story goes for open source, let's say forensic tools that are widely used.
I also think that it's very important that you also need to have some sort of standardization when it comes to automotive digital forensic. That doesn't exist today. So we don't have any guidelines or standard format for the data, for data collection when it comes to automotive digital forensics. So before we know how to use available tools, it's also important to move towards that direction as well, I believe.
Okay, another question? Yeah.
Can I?
Yeah, yes, I have a question. Now when both OEMs and Tier 1s have gone through the hurdle of cybersecurity certifications and stuff like that, what do you think will be the hurdle? How can you simplify the hurdle? Because I think you all have an uphill on the effort that is needed, the processes, the paperwork, everything between OEM, Tier 1, Tier 2. Do you have any ideas how that could actually be simplified, but still more be targeted against increasing security?
I don't have a good answer to that question, but what I would wish to happen is that they are not buried under paperwork, forgetting the fact that they need to also build secure and safe systems. Because a lot of these regulations that you follow, you generate evidence, you collect evidence, you show, you follow guidelines, and then you show documentations. But there could be a mismatch between what the documentation, not that you falsify documentation, but you do it for the basic minimum requirement and not necessarily showing the exact functionality or the features that your system have. So that's one thing that I see as a concern. And the other thing that I see as a concern is this interaction between different dependability attributes. We talk now about resilience. There are acts on it in different domains being discussed at. But resilience is not only about cybersecurity. All the other dependability attributes that exist, safety, reliability, availability, you can have a resilient system with respect to each of these attributes. To one person, resilience might be that I want my privacy to be resilient. But to many people, resilience might have something to do with safety. And I do not think that, going back to the education part that we talked about in the morning with Pontus, I don't think that people, even experts who are collecting evidence, have a good overview over all these different aspects. And we need to work on that, I think.
If I understood your question correctly, your question was how could we simplify, hopefully going forward. I would say, personally, I think integrating security as like a just normal aspect of quality during development. The reason I say this is that I think still security is being seen as an add-on, an afterthought in many cases, and that would create problems. So I think if we could really achieve, and this is actually a really hard goal to achieve, to integrate security as like a normal aspect of development. It sounds easy on the surface, but it's actually quite challenging. But if we could achieve that, then I think it will actually simplify a lot of stuff. And in addition to that, just like Beru said, I think there is quite a lot of need for awareness raising and education within this area.
Okay, thank you very much. I think we're running out of time, and as always, I have lots of questions left myself, but I'm happy that you had long discussions among yourselves. So let's give the attendees an applause. Thank you very much.
So I would just like to say a few words to wrap up the day. So I hope many of you can stay for a little bit longer because we have a poster session outside in the foyer, and there will be some drinks and nibbles, and you will have a chance to see some of the research by the PhD students here at Chalmers, so the next generation security experts. So I hope you will stay for that. But otherwise, I just want to say thank you to all the speakers, all the panelists, also all the people who've been helping me share sessions, carrying the mics, our technicians in the back, thank you very much. Everything's been running smoothly. And I also would like to say a special thank you to Ulrika Avedal-Årberg, who's been our event manager. So a big hand of applause for all these people. And with that, I would like to conclude this seminar. Please do go and see the poster and continue to mingle. Thank you very much.